Tonight, we're going to explore a concept so strange, so counterintuitive, that it has driven mathematicians insane, sparked religious debates for millennia, and continues to break the minds of the smartest people on Earth: infinity. You've heard this word thousands of times. You probably think you understand it. It's just something that goes on forever, right? Something without end. Simple enough. But here's what most people don't realize. When you actually understand what infinity means, when you truly grasp the depths of this concept, it doesn't just change how you see numbers. It changes how you see reality itself. It's not just a big number. It's not just something that keeps going. Infinity is a concept so profound, so paradoxical, that it challenges the very foundations of logic, mathematics, and human understanding. And by the end of this journey, you're going to understand why some infinities are bigger than others. Yes, you heard that right. Some infinities are larger than other infinities. That sentence sounds like nonsense, like something a philosopher might say after too much wine. But it's mathematically proven, rigorously demonstrated, and absolutely true. And once you understand why, you'll never think about numbers, space, time, or existence the same way again. Let's begin with something familiar: counting. You understand counting in your everyday life. You learned it as a child, probably one of the first intellectual skills you ever mastered. 1, 2, 3, 4, 5. You count the toys on your shelf, the steps on the staircase, the candles on your birthday cake. These are numbers you can relate to because you've used them. You have a sense of what they mean in terms of quantity, in terms of real objects in the real world. When someone tells you there are 5 apples in the basket, you know exactly what that means. You can picture those apples. You can hold them. You can count them yourself and verify. The number 5 corresponds to something concrete and tangible. This is how we first learn about numbers, through counting physical things. And for most of human history, this was the only kind of mathematics that existed. Numbers were tools for counting sheep, measuring land, tracking days. They were practical instruments tied to the physical world. But here's the question that changes everything. A question so simple that children ask it, yet so profound that the greatest minds have struggled with it for thousands of years. When does counting stop? Think about it for a moment. You count 1, 2, 3, 4, 5, and you keep going. 6, 7, 8, 9, 10. You could keep counting all day. 11, 12, 13. You could count for weeks, for months, for years. But when do you reach the end? When do you arrive at the last number, the final destination, the point where you can say, "That's it. I've counted everything there is to count"? The answer, of course, is never. There is no last number. For any number you can name, no matter how large, you can always add one more. 1 million? Add 1 and get 1,000,001. 1 billion? 1 billion and 1. 1 trillion? 1 trillion and 1. There is always another number waiting. Always another step on an endless staircase. This is something you probably realized as a child. Maybe you asked your parents, "What's the biggest number?" And they told you there isn't one. Numbers go on forever. You might have accepted this answer and moved on with your life. But let me tell you something. That moment, that childhood realization that numbers never stop, was your first encounter with infinity. And you probably didn't realize just how strange and terrifying that encounter truly was. Let me try to give you a sense of what infinity means by starting with numbers we can almost comprehend. 1 million is 1,000 thousands. If you saved $1 every single day, starting today and continuing without fail, you'd have $1 million in about 2,740 years. That's a long time, longer than the Roman Empire lasted, longer than Christianity has existed. You'd have to have started saving during the late Bronze Age, when the Trojan War was supposedly fought, to have $1 million by now. But at least you can imagine a timeline stretching back that far. It's conceivable. It connects to human history. 1 billion is 1,000 millions. Now we're in different territory entirely. If you saved $1 every second, not every day but every single second, you'd need about 32 years to save $1 billion. Think about that. A million seconds is about 11.5 days. You can imagine 11.5 days. That's a vacation. But a billion seconds is 32 years. The jump from a million to a billion is enormous. It's the difference between a week and a half and an entire adult lifetime. A trillion is 1,000 billions. And here's where numbers start to completely disconnect from anything we can relate to. If you counted to a trillion, one number per second, without stopping to sleep or eat or rest, it would take you about 31,700 years. Let me put that in perspective. 31,700 years ago, modern humans were living in the last ice age. We were using stone tools. We were hunting woolly mammoths and giant ground sloths. We hadn't invented agriculture. We hadn't built cities. We didn't have writing or mathematics or philosophy. We lived in small tribal groups, following animal herds across frozen landscapes. The first cave paintings at Lascaux wouldn't be created for another 15,000 years. The wheel wouldn't be invented for another 26,000 years. To count to a trillion, you would have needed to start before any of that. Before civilization, before history, before almost everything that makes us human in the modern sense. You'd have been counting through the entire development of human society, through the invention of farming, through the rise and fall of every empire, through every war and peace and discovery and catastrophe in human history. And you'd still be counting today, and you'd still have thousands of years to go. But here's the thing about infinity. You could never reach it, not in a trillion years, not in a trillion years, not if you counted for longer than the universe has existed. Because infinity isn't a number you can reach. It's not a destination at the end of a very long journey. It's something else entirely. And this is where most people's understanding of infinity breaks down. Most people think infinity is just a really, really big number. The biggest number imaginable. Something beyond millions and billions and trillions, something so large that we can't comprehend it, but still fundamentally a number like any other. This is wrong, completely and fundamentally wrong. Infinity is not a number at all. It doesn't behave like a number. It doesn't follow the rules that numbers follow. When mathematicians say infinity, they're not pointing to something at the far end of the number line. They're pointing to a concept, an idea about endlessness itself. And that concept, when you examine it closely, does things that seem absolutely impossible. Consider this. If infinity were a number, what would happen if you added 1 to it? If infinity is the biggest thing there is, then infinity plus 1 should be, what? Bigger than infinity? But infinity is supposed to be the biggest. There can't be anything bigger. So maybe infinity plus 1 equals infinity. That seems reasonable. Adding a finite amount to something infinite shouldn't change it. But wait, if infinity plus 1 equals infinity, then we can do some algebra. Subtract infinity from both sides of the equation. We get 1 equals 0. But 1 doesn't equal 0. 1 and 0 are different numbers. So something has gone terribly wrong. The rules of arithmetic that you've relied on your entire life, the rules that let you balance checkbooks and calculate tips and figure out how to split the bill at a restaurant, these rules break down completely when infinity enters the picture. Infinity isn't just a big number. Infinity is a different kind of thing entirely. And working with it requires completely different rules. The ancient Greeks recognized this problem over 2,000 years ago. They were brilliant mathematicians who developed geometry and proved theorems and laid the foundations for everything that came after. But infinity terrified them. The philosopher Aristotle, one of the greatest thinkers in human history, tried to diffuse the danger by making a crucial distinction. He separated what he called potential infinity from actual infinity. Potential infinity is a process that can continue without end. You can always add one more. You can always take another step. The process never finishes, but at any given moment, you've only completed a finite number of steps. Actual infinity is different. Actual infinity would be a completed infinite thing, not a process that goes on forever, but a finished object that contains infinitely many parts. Aristotle accepted potential infinity, but rejected actual infinity as impossible. Most mathematicians for the next 2,000 years agreed with him. They used infinity as a convenient shorthand, a way of talking about processes that continue without limit. But they didn't treat infinity as a real thing that could be manipulated and calculated with. They were afraid of it. They sensed that actual infinity contained paradoxes and contradictions that could tear logic apart. And as we'll see, they had very good reason to be afraid. Why should you care about any of this? Why does infinity matter outside of abstract mathematics? Because infinity isn't just abstract, it touches everything. Every time you use a smartphone, you're relying on mathematics built on infinity. The processors in your phone use algorithms designed with calculus, and calculus is fundamentally about infinity. It's about what happens when you divide things into infinitely small pieces, or add up infinitely many terms. Without infinity, there's no calculus. Without calculus, there's no physics. Without physics, there's no technology. The bridge you drive across, the airplane you fly in, the medicine you take, the building you live in, all of these were designed using mathematical tools that require infinity. When you ask whether the universe goes on forever, whether space extends without limit, you're asking about infinity. Cosmologists and physicists wrestle with this question constantly. Is the universe infinite or finite? Does it have an edge, or does it stretch on forever? The answer has profound implications for everything from the fate of existence to the possibility of alien life. When you think about time, about whether the past extends infinitely backward or the future extends infinitely forward, you're grappling with infinity. These aren't just philosophical puzzles, they're questions about the fundamental nature of reality. And then there are the personal questions. The questions that keep people awake at night. Is there life after death? Could consciousness continue forever? Would you even want to live for eternity if you could? What would it mean to experience infinite time? These questions might seem separate from mathematics, but they're not. They're all questions about infinity, about what it would mean for something to go on without end, about whether endless existence would be a blessing or a curse. Infinity isn't just a concept in a textbook. It's woven into the deepest questions humans have ever asked. Questions about the nature of existence, the structure of reality, the meaning of life and death. Understanding infinity, or at least understanding why infinity resists understanding, is essential to grappling with these questions honestly. So where are we going tonight? We're going to take a journey through the strange landscape of infinity. We'll start with the oldest paradoxes, puzzles that tortured ancient philosophers and still haven't been fully resolved today. We'll watch as some of history's greatest minds try and fail to tame the infinite. Then we'll meet the mathematician who finally succeeded, a man named George Cantor, who discovered truths so strange that many of his colleagues thought he'd gone mad. Maybe he had. He spent years in psychiatric hospitals, plagued by doubts and depression, but his ideas won. Today, Cantor's theory of infinity is the foundation of modern mathematics. And once you understand it, once you see what he saw, you'll realize that infinity is even stranger than you imagined. Because Cantor proved that some infinities are bigger than others. He proved that there's an infinite tower of infinities, each one larger than the last. And he proved that some questions about infinity can never be answered. Not because we're not smart enough, but because mathematics itself doesn't contain the answers. But first, we need to understand why infinity terrified the greatest minds in history. For that, we need to go back 2,500 years, to ancient Greece, where a philosopher named Zeno constructed puzzles so devious that we still haven't fully escaped them. To understand why infinity is so dangerous, we need to travel back to ancient Greece, to a time when philosophy and mathematics were young, when the foundations of Western thought were still being laid. The year is roughly 450 BCE. The place is Elea, a Greek colony in what is now southern Italy. And the philosopher we're meeting is a man named Zeno. Zeno of Elea was a student of Parmenides, one of the most influential and bizarre philosophers in ancient Greece. Parmenides taught something that seemed completely insane. He claimed that change was impossible. Motion was impossible. The world we see around us, with objects moving and transforming and coming into being and passing away, was an illusion. True reality was eternal, unchanging, and unified. There was no such thing as movement or transformation. There was only one eternal, motionless, undivided being. Now, you might think this is obviously wrong. Look around you. Things are clearly moving. The wind blows, birds fly, people walk, the sun crosses the sky. How could anyone deny the existence of motion? But Parmenides wasn't making a claim about appearances. He was making a claim about logic. He argued that if you tried to describe change and motion using pure reason, you ran into contradictions. Therefore, change and motion must be illusions, tricks of perception that don't reflect the true nature of reality. This was a radical philosophical position, and it attracted a lot of criticism. Other philosophers thought Parmenides was crazy. They pointed to everyday experience. They pointed to obvious cases of motion and change. Surely this was enough to refute him. Zeno came to his teacher's defense with a weapon more devastating than any philosophical argument that had come before. He constructed paradoxes. These weren't arguments for Parmenides' position. They were arguments against the common sense view. They were designed to show that if you believed in motion, if you believed in change, if you believed in plurality, in many separate things existing in space, then you faced contradictions just as severe as anything Parmenides had ever proposed. Zeno's paradoxes didn't prove that Parmenides was right. They proved that everyone was confused. They showed that our most basic concepts like motion and space and time, contained hidden contradictions that no one knew how to resolve. The most famous of Zeno's paradoxes is the tale of Achilles and the tortoise. Achilles was a hero of Greek mythology, the greatest warrior of the Trojan War, renowned for his speed and athletic prowess. In the story, Achilles is challenged to a race against a tortoise. Now this seems absurd. Achilles was the fastest runner in all of Greece. A tortoise is one of the slowest creatures on earth. The outcome should be obvious. Achilles should win easily, running circles around the tortoise while barely breaking a sweat. But the tortoise, being slow, is given a head start. Let's say the tortoise starts 100 meters ahead of Achilles. The race begins. Achilles sprints forward at tremendous speed. The tortoise plods along slowly. Common sense tells us what happens next. Achilles gains on the tortoise, catches up, passes it, and wins the race. Simple, obvious, undeniable. But Zeno says no. Zeno says that Achilles can never catch the tortoise. Not because the tortoise is fast, but because of the structure of space and motion itself. Here's the argument. Before Achilles can pass the tortoise, he must first reach the point where the tortoise started. That's 100 meters away. Let's say Achilles runs 10 times faster than the tortoise. In the time it takes Achilles to run those 100 meters, the tortoise has moved forward 10 meters. The tortoise is slow, but it's not standing still. So when Achilles reaches the tortoise's starting point, the tortoise is no longer there. It's 10 meters ahead. No matter, says Achilles, I'll just run those 10 meters. But in the time it takes Achilles to run 10 meters, the tortoise has moved forward 1 meter. The tortoise is still ahead. Achilles runs that 1 meter. The tortoise moves forward 1/10 of a meter. Achilles runs that 1/10 of a meter. The tortoise moves forward 1/100th of a meter. Do you see the pattern? Every time Achilles reaches where the tortoise was, the tortoise has moved a little bit farther ahead. The gap keeps shrinking, but it never disappears entirely. First 100 meters, then 10, then 1, then 1/10, then 100th, then 1,000th. The distances become incredibly small, but they never reach zero. There's always some tiny gap remaining. And as long as there's a gap, Achilles hasn't caught the tortoise. Achilles has to cover infinitely many distances. First the original 100 meters, then the 10-meter gap, then the 1-meter gap, then the 10th meter gap, and so on forever. Each of these distances takes some amount of time to cover. Achilles is fast, but he's not infinitely fast. Covering any distance, no matter how small, takes some amount of time, and he has infinitely many distances to cover. Infinite distances, each one taking time. How can a finite runner ever complete infinitely many tasks? How can any finite amount of time contain infinitely many intervals? You might be tempted to dismiss this with common sense. Obviously, Achilles catches the tortoise. We can see it happen. We can calculate when it happens using basic algebra. If Achilles runs 10 meters per second and the tortoise runs 1 meter per second and the tortoise starts 100 meters ahead, then Achilles catches the tortoise after 11 and 1/9 seconds at a distance of 111 and 1/9 meters. Problem solved. But Zeno would say that you haven't actually solved anything. You've just asserted the conclusion. Yes, Achilles catches the tortoise. Zeno isn't denying that. What he's asking is how. How can a runner complete infinitely many tasks in finite time? How can infinitely many intervals of time add up to a finite total? You can't just say obviously they do and call that an explanation. That's not philosophy. That's not logic. That's just avoiding the question. The mathematical answer involves infinite series. The distances Achilles must cover form a geometric series. 100 plus 10 plus 1 plus 1/10 plus 100th, and so on. This infinite series has a finite sum. The mathematics tells us what that sum is. But for the ancient Greeks, this mathematics didn't exist. They had no rigorous way to handle infinite sums. They couldn't prove that infinitely many terms could add up to something finite. The very idea seemed contradictory. How can you finish something that has no end? How can you complete infinitely many steps? Zeno had other paradoxes too. Consider the dichotomy, which is even more disturbing than Achilles and the tortoise. Suppose you want to walk across a room. Before you can reach the other side, you must first reach the halfway point. That's obvious. You can't get to the end without passing through the middle. But before you can reach the halfway point, you must reach the point 1/4 of the way across. You can't get to the middle without passing through the quarter point. Before you can reach the quarter point, you must reach the 1/8 point. Before the 8th, the 16th. Before the 16th, the 32nd. Do you see where this is going? Before you can take a single step, you must complete infinitely many preliminary tasks. You must reach the halfway point to where you're going, and before that the quarter point, and before that the 8th point, and so on forever. There's no first step you can take. Before any step, there's always a smaller step that must come first. You're not trying to finish an infinite sequence, you're trying to start one. And you can't even start, because there's no first element. The beginning of your journey is an infinite regress. It stretches backward forever, an endless sequence of preliminary tasks that must be completed before you can even begin. According to this logic, motion isn't just difficult to complete. Motion is impossible to initiate. You can't even begin to move, because beginning requires completing infinitely many tasks first. And yet, here you are. You moved your eyes across this page. You moved your hand to scroll or turn the page. You move all the time. So what's wrong with Zeno's argument? Where exactly does it fail? Then there's the arrow paradox, which attacks motion from a completely different angle. Consider an arrow in flight. At any single instant in time, where is the arrow? Think carefully. At any single moment, frozen in time like a photograph, the arrow occupies a specific position. It's right there, in that exact spot. It's not moving in that instant, because moving means changing position, and in a single instant, there's no time for change. In a single instant, the arrow is simply where it is. But here's the problem. Time is made up of instants. Every moment of time is an instant. If the arrow isn't moving at any particular instant, when does it move? Add up all the instants in the arrow's flight. At instant 1, the arrow is stationary. At instant 2, the arrow is stationary. At instant 3, stationary. At every single instant, the arrow is not moving. But if it's not moving at any instant, how can it be moving overall? How can a bunch of stationary states add up to motion? It's like saying that a bunch of zeros add up to something positive. 0 plus 0 plus 0, repeated forever, still equals 0. Stationary plus stationary plus stationary, repeated forever, should still equal stationary. And yet, the arrow moves. The arrow flies through the air and strikes its target. We can see it happen. So where is the error? These paradoxes might seem like clever tricks, logical puzzles designed to amuse and confuse, but they're much more serious than that. The ancient Greeks took logic seriously. If an argument was valid, if it followed the rules of reasoning correctly, then you had to accept its conclusion, no matter how absurd that conclusion seemed. You couldn't just wave your hands and say, obviously that's wrong. You had to find the specific flaw in the reasoning. You had to identify exactly where the argument went astray. And with Zeno's paradoxes, no one could do that. The arguments seemed valid. The premises seemed true. The logic seemed airtight. But the conclusions were clearly false. Motion exists. Achilles catches tortoises. Arrows fly. Something was deeply wrong, but no one could explain what. For 2,000 years, the greatest minds in human history struggled with Zeno's paradoxes. Aristotle, perhaps the most influential philosopher who ever lived, tried to resolve them by distinguishing between actual infinity and potential infinity. He argued that you could potentially divide space infinitely, but you never actually completed the division. At any moment, you'd only made finitely many divisions. This was a reasonable response, but it didn't fully resolve the paradoxes. It didn't explain how motion was possible, if completing motion required traversing infinitely many intervals. Medieval philosophers debated the paradoxes endlessly. They proposed solutions involving indivisible minima of space and time, or divine intervention, or various logical distinctions. None of these solutions were entirely satisfactory. The paradoxes persisted, nagging at the foundations of thought, suggesting that something was fundamentally wrong with our understanding of space, time, and infinity. In the 17th century, Isaac Newton and Gottfried Wilhelm Leibniz independently invented calculus. Calculus was a revolution. It provided mathematical tools for handling infinity in a systematic way. It let you work with infinitely small quantities and infinite sums. It let you calculate the exact moment when Achilles catches the tortoise and prove that the infinite series converges to a finite value. In some sense, calculus solved Zeno's paradoxes. It showed that infinitely many terms can add up to a finite total, that infinitely many intervals of time can constitute a finite duration. But even calculus didn't fully resolve the philosophical issues. Newton and Leibniz used infinitesimals, infinitely small quantities, without rigorously defining what they were. Critics attacked calculus as logically incoherent. Bishop Berkeley famously asked whether infinitesimals were the ghosts of departed quantities. The foundations of calculus remained shaky for another 200 years, until mathematicians like Cauchy and Weierstrass developed the rigorous theory of limits. And even then, even after calculus was placed on solid logical foundations, Zeno's paradoxes continued to provoke debate. The deep issue is this: Zeno's paradoxes force us to confront questions about the nature of space and time that mathematics alone cannot answer. Is space infinitely divisible? Or is there some smallest unit of distance? Is time continuous, flowing smoothly like a river? Or is it discrete, jumping from moment to moment like frames in a film? These are questions about physics, about the actual structure of reality. Mathematics can tell us what's logically possible. It can't tell us which possibility describes our universe. Modern physics, particularly quantum mechanics, suggests that space and time might indeed be discrete at very small scales. There might be a smallest possible length, the Planck length, about 1.6 times 10 to the negative 35th meters. There might be a smallest possible duration, the Planck time, about 5.4 times 10 to the negative 44th seconds. If space and time are discrete, then Zeno's paradoxes dissolve. You can't divide space infinitely if space comes in indivisible chunks. You can't have infinitely many moments if time jumps from one discrete instant to the next. But we don't know for certain whether space and time are discrete. We don't have direct experimental evidence one way or the other. The question remains open. What Zeno's paradoxes show is that infinity is dangerous. When you let infinity into your reasoning, strange things happen. Logic that seems perfectly valid produces conclusions that seem perfectly absurd. Concepts that seem perfectly clear turn out to be deeply puzzling. Motion, space, time, these are things we experience every day. We think we understand them, but when you examine them closely, when you push them to their infinite limits, they reveal hidden depths that resist easy comprehension. Zeno didn't solve the problem of infinity. He exposed it. He showed that infinity was lurking in our most basic concepts, waiting to create paradoxes. And for 2,000 years, mathematicians were afraid to confront it directly. They used infinity when they had to, but they treated it like a dangerous tool that might explode in their hands. They kept it at arm's length. They never looked too closely at what it really was. But there were hints along the way. Hints that infinity might be even stranger than Zeno imagined. Hints that the real paradoxes were still waiting to be discovered. And the first person to glimpse these deeper mysteries was a scientist you might not expect to find thinking about pure mathematics. A man who spent most of his life studying planets and falling objects and the laws of motion. His name was Galileo Galilei. And in 1638, while under house arrest for the crime of believing the Earth moved around the sun, he wrote down an observation about infinity that would puzzle mathematicians for another 250 years. He noticed something that seemed impossible. He noticed that part of infinity could be equal to the whole. The year is 1638. The place is a villa in Arcetri, a small town in the hills above Florence, Italy. An old man sits in a chair, nearly blind now, his eyes ruined by years of staring at the sun through telescopes. He is 74 years old, and he is a prisoner. The Roman Inquisition has confined him to house arrest for the crime of teaching that the earth moves around the sun, a doctrine the church has declared heretical. He will never leave this villa again. He will die here in 4 years, isolated from the scientific community he helped create, forbidden from publishing new work in Italy. But his mind remains sharp, and in this villa, dictating to his students because his eyes can no longer read or write, Galileo Galilei composes his final masterpiece. He calls it Discourses and Mathematical Demonstrations relating to 2 new sciences. It's a book about physics, about the science of motion and the science of materials. But tucked away in its pages is something else entirely, a puzzle about infinity that would haunt mathematics for centuries. Galileo was not primarily a mathematician. He was a physicist, an astronomer, an experimenter. He dropped balls from towers to study how objects fall. He built telescopes and discovered the moons of Jupiter. He observed sunspots and the phases of Venus. He championed the Copernican model of the solar system at a time when doing so was dangerous. But Galileo understood that physics required mathematics, that understanding the natural world meant understanding the abstract relationships between quantities. And in the course of his work, he stumbled upon something strange, something about infinity that didn't make sense. "Consider the counting numbers," he said. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on forever. These are the most basic objects in mathematics, the foundation upon which everything else is built. Everyone knows the counting numbers. Everyone can recite them, at least the first few hundred or thousand. They stretch out to infinity, an endless sequence that never terminates. Now consider the perfect squares. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100. These are the numbers you get when you multiply a counting number by itself. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9, 4 times 4 is 16, and so on. The perfect squares are also infinite in number. There's no largest perfect square, just as there's no largest counting number. For any square you can name, you can always find a bigger one. The sequence goes on forever. But here's the puzzle that troubled Galileo. Which set is larger, the counting numbers or the perfect squares? Think about it for a moment before reading on. Common sense gives an obvious answer. The counting numbers must be larger. After all, the perfect squares are just some of the counting numbers. 1 is both a counting number and a perfect square. But 2 is a counting number that isn't a perfect square. 3 is a counting number that isn't a perfect square. 5, 6, 7, 8, all counting numbers, none of them perfect squares. The counting numbers include all the perfect squares, plus many other numbers besides. The squares are a part of the counting numbers. A subset. The part should be smaller than the whole. This is one of the most basic principles of reasoning. If you have a basket of fruit containing apples and oranges and bananas, the apples alone are fewer than all the fruit together. The part cannot equal the whole. The part is always smaller. This seems absolutely obvious, completely undeniable, as certain as anything in logic or mathematics. And yet, Galileo noticed something troubling. You can pair up the counting numbers with the perfect squares in a very systematic way. Take 1 and pair it with 1 squared, which is 1. Take 2 and pair it with 2 squared, which is 4. Take 3 and pair it with 3 squared, which is 9. Take 4 and pair it with 4 squared, which is 16. Take 5 and pair it with 25. Take 6 and pair it with 36. Do you see the pattern? Every counting number gets paired with exactly 1 perfect square, and every perfect square gets paired with exactly 1 counting number. 1 pairs with 1, 2 pairs with 4, 3 pairs with 9, 100 pairs with 10,000, 1,000,000 pairs with 1 trillion. No counting number is left without a square partner. No perfect square is left without a counting number partner. The pairing is perfect, complete, exhaustive. Every element on one side matches with exactly 1 element on the other side. But if 2 sets can be paired up perfectly, with nothing left over on either side, doesn't that mean they're the same size? If you have a row of chairs and a row of people, and every chair has exactly 1 person sitting in it, and every person is sitting in exactly 1 chair, then you have the same number of chairs and people. You don't need to count them to know this. The perfect pairing proves equality. This works for finite sets. 5 chairs paired with 5 people means 5 of each. 100 chairs paired with 100 people means 100 of each. But Galileo has just shown that the counting numbers can be perfectly paired with the perfect squares. Does that mean they're the same size? But that's impossible. The squares are just a part of the counting numbers. The part can't equal the whole, yet the pairing exists. The pairing is undeniable. You can verify it yourself. Every counting number n pairs with n squared. Every perfect square, n squared pairs with its square root n. The correspondence is perfect. Galileo saw only one way out of this contradiction. He concluded that concepts like larger, smaller, and equal simply don't apply to infinite sets. When you're dealing with finite collections, you can compare their sizes. You can say one is bigger than another, or that they're equal. But when you're dealing with infinity, these concepts break down. They become meaningless. Infinite sets are simply incomparable. You can't ask whether one infinity is bigger than another, because the question doesn't make sense. The language of comparison, developed for finite things, fails when applied to the infinite. This was a reasonable response to the paradox. It was, in fact, the standard response for the next 2.5 centuries. Mathematicians noted Galileo's puzzle, acknowledged that infinity was strange, and mostly avoided the issue. They used infinity when they needed it, in calculus and analysis and geometry, but they didn't try to develop a systematic theory of infinite sets. They didn't try to compare infinities or classify them or understand their properties. The subject was too dangerous, too paradoxical. Better to leave it alone. But Galileo's puzzle kept nagging at the mathematically curious, because the same strange phenomenon appeared everywhere you looked. Consider the even numbers. 2, 4, 6, 8, 10, 12. These are just the counting numbers that are divisible by 2. Half of all counting numbers are even. The other half are odd. So there should be half as many even numbers as counting numbers, right? But you can pair them up perfectly. 1 pairs with 2, 2 pairs with 4, 3 pairs with 6, 4 pairs with 8. Every counting number n pairs with the even number 2n. Every even number pairs with exactly 1 counting number. If perfect pairing means equality, then there are as many even numbers as counting numbers, even though the even numbers are only half of the counting numbers. The part equals the whole again. Consider the integers. These include all the counting numbers, but also 0 and all the negative numbers. -1, -2, -3, stretching off to negative infinity. The integers seem much more numerous than the counting numbers. They extend in both directions, whereas the counting numbers extend in only one direction. You might think there are twice as many integers as counting numbers, or perhaps infinitely more, but you can pair them up. 0 pairs with 1, 1 pairs with 2, -1 pairs with 3, 2 pairs with 4, -2 pairs with 5, 3 pairs with 6, -3 pairs with 7. The pattern is, take the counting numbers and alternate between non-negative integers and negative integers. 0, 1, -1, 2, -2, 3, -3. Every integer gets a unique counting number. Every counting number corresponds to a unique integer. Perfect pairing, same size. Even though the integers seem twice as large, extending in both directions instead of one. What about rational numbers? These are fractions, ratios of integers: 1/2, 2/3, 3/4, 7/5, -11/13. Between any two rational numbers, no matter how close together, there are infinitely many more rational numbers. Between 0 and 1, there are infinitely many fractions. Between 0 and 1/10, infinitely many more. The rationals are dense, they're packed together infinitely tightly. Surely there must be more rationals than counting numbers. Surely this denser, more complex set must be larger. But no, there's a way to pair them up too. Arrange the positive fractions in a grid. The first row contains all fractions with numerator 1. 1/1, 1/2, 1/3, 1/4. The second row contains all fractions with numerator 2. 2/1, 2/2, 2/3, 2/4, and so on. Now trace a diagonal path through this grid, zigzagging back and forth. 1/1, then 2/1, then 1/2, then 1/3, then 2/2, then 3/1, then 4/1, then 3/2, then 2/3. You traverse the entire grid, hitting every fraction eventually, and you can number them as you go. First fraction, second fraction, third fraction, skip duplicates like 2/2, which equals 1/1. You end up pairing every positive rational with a counting number. Extend the method to include negative rationals and 0, and you've paired all the rationals with all the counting numbers. Same size again. Everything seems to be the same infinity. The counting numbers, the even numbers, the squares, the integers, the rationals, they all pair up perfectly with each other. No matter how much bigger one set seems, no matter how much smaller another appears, they all turn out to have the same size when you find the right pairing. Is there only one infinity then? Is the infinity of counting numbers the only infinity there is, and all infinite sets are the same size? For 250 years after Galileo, mathematicians either assumed this was true or avoided the question entirely. Infinity was infinity. There was only one kind. It was strange and paradoxical, as Galileo had shown, but at least it was unified. At least you didn't have to worry about different sizes of infinity, about comparing one infinite set to another. That would be absurd. That would be chaos. That would break mathematics entirely. And then came George Cantor, a German mathematician working in the 1870s. Cantor asked a question that seemed almost naive. He asked whether there might be different sizes of infinity. He asked whether some infinite sets might be genuinely, provably, rigorously larger than others. And what he discovered shattered everything mathematicians thought they knew about infinity. He proved that Galileo was wrong. You can compare infinite sets. Some infinities are bigger than others. And the Tower of Infinities stretches up forever, infinity after infinity, each one dwarfing the last. The mathematical universe was infinitely larger than anyone had imagined. And Cantor's proof was so simple, so elegant, so devastating, that anyone who understood it could never see infinity the same way again. George Ferdinand Ludwig Philipp Cantor was born on March 3, 1845, in St. Petersburg, Russia. His father was a successful merchant, a man of deep religious conviction who believed that God had special plans for his talented son. His mother came from a family of musicians, and young George showed early promise in that direction. He played the violin beautifully and could have pursued a career in music, but mathematics called to him more strongly. When the family moved to Germany in 1856, seeking a better climate for the father's health, George found himself immersed in a mathematical culture that was the finest in the world. Germany in the 19th century was the center of mathematical research. The great universities at Göttingen, Berlin, and elsewhere attracted brilliant minds from across Europe. Here, mathematics was not just a tool for engineering or commerce. It was a subject worthy of study for its own sake, a realm of pure thought where rigor and creativity combined to uncover eternal truths. Cantor studied at the University of Berlin under some of the greatest mathematicians of the age: Ernst Kummer, Leopold Kronecker, Karl Weierstrass. These men were giants, each responsible for fundamental advances in algebra, analysis, and the foundations of calculus. Cantor absorbed their teachings eagerly. He earned his doctorate in 1867 with a dissertation on number theory, and he began his academic career at the University of Halle, a respectable but not prestigious institution. He would remain at Halle for his entire career, never obtaining the position at a major university that he craved and felt he deserved. This was partly due to academic politics, partly due to personality conflicts, and partly, perhaps, due to the radical nature of his ideas. But we're getting ahead of ourselves. In his early years, Cantor worked on relatively conventional problems in analysis. He studied trigonometric series, the mathematical objects used to represent periodic phenomena like sound waves and vibrations. This work led him, almost by accident, to think about the nature of infinite sets. To understand certain properties of functions, he needed to understand the sets on which those functions were defined. And the sets he encountered were infinite, not just potentially infinite, in Aristotle's sense, but actually infinite. Completed infinities, with infinitely many members, all existing at once. Most mathematicians treated such sets gingerly, if they treated them at all. But Cantor was different. He was bold. He was willing to ask questions that others considered meaningless or dangerous, and the question he asked was revolutionary. Given two infinite sets, is there a way to determine whether they have the same size? And if they don't have the same size, can we say which one is larger? Now, you might think this question makes no sense. Galileo had argued that infinite sets couldn't be compared. They were all just infinite, and that was that. But Cantor realized that Galileo had actually provided the key to comparing infinite sets. Galileo had used pairing. He had shown that the counting numbers and the perfect squares could be paired up perfectly, 1 to 1, and he had concluded that this meant the usual notions of size didn't apply. But what if you looked at it differently? What if perfect pairing did mean that two sets were the same size? This would be strange, yes. It would mean that an infinite set could be the same size as one of its proper parts. But maybe that's just how infinity works. Maybe that's what makes infinity special. An infinite set is precisely a set that can be put into one-to-one correspondence with a proper subset of itself. This isn't a paradox to be avoided. It's a definition to be embraced. It tells us what infinity means. Cantor developed this idea rigorously. He defined two sets as having the same cardinality, the same size, if and only if there exists a one-to-one correspondence between them. A function that pairs each element of one set with exactly one element of the other, and vice versa, with nothing left over on either side. For finite sets, this gives the usual notion of size. A set of 5 elements has the same cardinality as any other set of 5 elements, but for infinite sets, strange things happen. The counting numbers have the same cardinality as the even numbers, because you can pair them up perfectly. The counting numbers have the same cardinality as the integers, and the same cardinality as the rational numbers. All of these infinite sets are the same size. In Cantor's precise sense, Cantor called this size countably infinite. A set is countably infinite if you can list its elements in a sequence, first, second, third, fourth, and so on. You might never finish the list, but every element eventually appears somewhere on it. The counting numbers are countably infinite by definition. Any set that can be paired with the counting numbers is also countably infinite. And as we've seen, many sets that seem larger or more complex than the counting numbers turn out to be countably infinite as well. But here's where Cantor made his revolutionary discovery. He asked whether all infinite sets are countably infinite. Are there sets so large that they can't be listed, can't be counted, can't be paired with the counting numbers? Galileo's examples suggested that the answer was no. Every infinite set he considered turned out to be countable. Maybe that was just how infinity worked. Maybe countable infinity was the only infinity there was. Cantor proved this was wrong. He proved that there are uncountable sets, infinite sets that are strictly larger than the counting numbers. Sets so vast that no list can contain them, no matter how cleverly constructed. The first example he found was the set of real numbers. Real numbers are all the numbers on the number line. They include the counting numbers, the integers, the rationals, but also the irrational numbers like the square root of 2 and pi and e. Irrational numbers can't be expressed as fractions. Their decimal expansions go on forever without repeating. The square root of 2 is approximately 1.41421356237, and the digits continue indefinitely with no pattern. Pi is approximately 3.141596535897932384626433, and again the digits continue forever without repeating. There are infinitely many irrational numbers. In fact, in a certain precise sense, almost all real numbers are irrational. The rationals, despite being dense, despite filling every gap between counting numbers with infinitely many fractions, are actually quite rare among the reals. They're like the rational grains of sand on an irrational beach that stretches beyond all comprehension. Cantor proved that the real numbers cannot be counted. There is no way to list them, no way to pair them with the counting numbers. The infinity of real numbers is strictly larger than the infinity of counting numbers. This is one of the most important and surprising results in all of mathematics, and Cantor proved it with an argument of stunning elegance. The proof is called the diagonal argument, and once you understand it, you will never think about infinity the same way again. Suppose someone claims to have a complete list of all real numbers between 0 and 1. Each real number can be written as an infinite decimal, 0.3729186, and so on. Some decimals terminate, like 0.5, but we can write this as 0.50000 with infinitely many zeros at the end. So every real number between 0 and 1 corresponds to an infinite sequence of digits after the decimal point. Now suppose we have a list of all such numbers. The list might look something like this. Number 1 on the list is 0.52348766149, and then more digits continuing forever. Number 2 is 0.184729386, and more digits. Number 3 is 0.9912384721, and more. Number 4 is 0.3748291853, and more. And so on. With infinitely many numbers on the list, each number having infinitely many digits. Now Cantor performs his devastating trick. He constructs a new number that cannot be on the list. He goes down the diagonal. He looks at the first digit of the first number. In our example, that's 5. He changes it to something different. Let's say he adds 1, wrapping around if necessary. So 5 becomes 6. He looks at the second digit of the second number, that's 8. He changes it. 8 becomes 9. He looks at the third digit of the third number, that's 1. 1 becomes 2. Fourth digit of the fourth number, 8 becomes 9. Fifth digit of the fifth number, 2 becomes 3. He continues this process forever, looking at the nth digit of the nth number and changing it to something else. The result is a new decimal. In our example, it starts 0.69293 and continues with different digits from each diagonal position. Here is the key observation. This new number is not on the list. It can't be the first number on the list, because it differs from the first number in the first decimal place. It can't be the second number because it differs from the second number in the second decimal place. It can't be the nth number for any n because it differs from the nth number in the nth decimal place. The new number differs from every single number on the supposedly complete list. Therefore, the list is not complete. We assumed we had a list of all real numbers between 0 and 1, and we proved that assumption leads to a contradiction. Any such list necessarily misses at least one number. But this argument works for any proposed list. No matter how you try to list the real numbers, the diagonal argument produces a number you missed. Therefore, no complete list is possible. Therefore, the real numbers are uncountable. Therefore, the infinity of real numbers is strictly larger than the infinity of counting numbers. Let that sink in for a moment. There are different sizes of infinity. The infinity of counting numbers is one size. The infinity of real numbers is a larger size. Not just slightly larger, not just a bit more numerous. Fundamentally, categorically, provably larger. You cannot pair them up. You cannot establish a one-to-one correspondence. No matter how clever you are, no matter what tricks you try, there will always be real numbers left over. There aren't enough counting numbers to label all the reals. The real numbers overflow any attempt to count them. Cantor gave these sizes names. The cardinality of the counting numbers, the smallest infinity, he called Aleph Null, using the first letter of the Hebrew alphabet with a subscript 0. This was a deliberate choice. Cantor was deeply religious, and he chose Hebrew letters to represent infinities because he associated infinity with the divine. The cardinality of the real numbers he called the cardinality of the continuum, often denoted by the letter C, and he proved that C is strictly greater than Aleph Null, not equal, as Galileo might have expected. Greater, larger, a bigger infinity. The mathematical community's reaction to Cantor's discoveries was mixed. Some mathematicians recognized immediately that Cantor had achieved something profound. They saw that his theory of infinite sets opened up entirely new areas of mathematics, provided rigorous foundations for analysis and topology, and answered questions that had puzzled thinkers for millennia. But others were hostile, deeply, virulently hostile. Cantor's former teacher, Leopold Kronecker, was particularly vicious. Kronecker believed that only the natural numbers were truly real. Everything else, fractions, irrational numbers, infinite sets, was a human construction, useful perhaps, but not genuinely mathematical. He called Cantor a corrupter of youth, a charlatan, a scientific fraud. He used his influence to block Cantor's career advancement, to prevent him from obtaining a position at a prestigious university, to undermine his reputation at every turn. The attacks took their toll. Cantor had always been sensitive, always craved recognition and approval. The hostility from established mathematicians, especially his former mentor, wounded him deeply. In 1884, he suffered his first serious mental breakdown. He was hospitalized for depression. He recovered and returned to work, but the breakdowns recurred throughout his life. He spent extended periods in psychiatric facilities. He doubted himself, doubted his work, wondered if Kronecker was right, and he had devoted his life to nonsense. The strange thing was that Cantor never doubted the truth of his results. The proofs were solid. The logic was impeccable. What he doubted was whether he had the right to discover them, whether he was worthy of the truths he had uncovered. He believed his mathematics came from God, that he was merely the instrument through which divine truths entered the world. And when the world rejected those truths, he felt he had failed in his sacred mission. Cantor did not stop with proving that the reals are larger than the naturals. He asked whether there were still larger infinities, and he proved that there were. Given any infinite set, you can always construct a larger one. The method involves what's called the power set. The power set of any set S is the set of all subsets of S. If S contains 3 elements, say 1, 2, and 3, then the power set contains 8 elements. The empty set, the set containing just 1, the set containing just 2, the set containing just 3, the set containing 1 and 2, the set containing 1 and 3, the set containing 2 and 3, and the set containing all 3. For any finite set with n elements, the power set has 2 to the n elements, but Cantor proved something remarkable. The power set of any set, finite or infinite, is strictly larger than the original set. You cannot pair a set with its power set. There will always be subsets left over. This means there is no largest infinity. Given any infinite set with cardinality alpha, the power set has a larger cardinality, and you can take the power set of the power set and get something larger still, and so on forever. The Tower of Infinities rises without end, infinity upon infinity, each one dwarfing everything below it. Cantor proved this using a clever argument, similar in spirit to the diagonal argument. Suppose you could pair up a set S with its power set. Then every element x in S would correspond to some subset of S. Consider the set of all elements that are not members of their corresponding subsets. Is this set the correspondent of any element? It can't be. If it were, call that element Y. Then we could ask, is Y a member of its corresponding set? If yes, then by definition of our constructed set, Y is not in it. If no, then by definition, Y is in it. Either way, contradiction. So no such pairing can exist. The power set is always strictly larger. Cantor spent his later years developing his theory further, exploring the implications, trying to prove additional results. One question in particular obsessed him. Is there an infinity between Aleph null and the continuum? We know the continuum is larger than the countable infinity, but is it the next largest infinity, or are there infinities in between? Cantor believed there was no in-between infinity. The continuum should be Aleph 1, the next infinite cardinal after Aleph null. This conjecture is called the continuum hypothesis. Cantor worked on it for years, trying to prove it, trying to find an intermediate infinity or prove none existed. He never succeeded. The failures contributed to his breakdowns. The continuum hypothesis became his white whale, the problem he could never solve no matter how hard he tried. He didn't know, couldn't have known, that the continuum hypothesis was unsolvable. Not just difficult, but actually undecidable within standard mathematics. In 1940, the logician Kurt Gödel proved that you cannot disprove the continuum hypothesis using the standard axioms of set theory. It's consistent with mathematics as we know it. In 1963, Paul Cohen proved that you cannot prove the continuum hypothesis either. It's independent of the standard axioms. You can add it as an axiom, and mathematics remains consistent. You can add its negation, and mathematics remains consistent. The question has no answer within the system. Mathematics itself doesn't determine whether there's an infinity between the countable and the continuum. Either answer is compatible with everything else we know. This was a stunning result, a demonstration that mathematics contains fundamental questions that mathematics cannot answer. Cantor spent his life torturing himself over a problem that was literally unsolvable. George Cantor died on January 6, 1918, in a sanatorium in Halle. He was 72 years old. His final years had been spent in and out of mental institutions, plagued by depression, struggling with the doubt that had haunted him since Kronecker's attacks. He never achieved the academic recognition he craved during his lifetime. He never obtained that prestigious position at Berlin or Göttingen. He died uncertain whether his life's work was revelation or madness, but his work survived. In the decades after his death, Cantor's theory of infinite sets became the foundation of modern mathematics. Set theory underlies virtually every branch of mathematics today. Logic, analysis, algebra, topology, all are built on the framework Cantor created. The mathematician David Hilbert, one of the most influential figures of the 20th century, called Cantor's theory the finest product of mathematical genius and one of the supreme achievements of purely intellectual human activity. No one shall expel us, Hilbert declared, from the paradise that Cantor has created. Today, every mathematics student learns Cantor's diagonal argument, Every serious mathematician works within the framework of infinite set theory. The concepts that drove Cantor to breakdown and despair are now standard, routine, part of the basic vocabulary of mathematical thought. He was vindicated, completely and absolutely, but too late for him to know it. The man who counted infinity never saw how completely his vision would triumph. He knew only the struggle, the doubt, the attacks from colleagues who thought him mad. The paradise he created was enjoyed by others. We left George Cantor having proved something that seemed impossible. Some infinities are bigger than others. The infinity of real numbers is strictly larger than the infinity of counting numbers. You cannot pair them up. You cannot establish a correspondence. The reals overflow any attempt to count them, spilling over the edges of any list you might construct. This was revolutionary enough. This alone would have secured Cantor's place in the history of mathematics. But he didn't stop there. He couldn't stop there, because once you accept that there are different sizes of infinity, an obvious question emerges. How many sizes are there? We know there's the countable infinity, the size of the counting numbers. We know there's the uncountable infinity of the real numbers. Which is larger? Are these the only two sizes? Or are there more? Is there a largest infinity, some ultimate infinite that encompasses everything else? Or does the hierarchy continue forever? Infinity upon infinity, each one dwarfing the last. Cantor answered this question decisively. There is no largest infinity. Given any infinite set, no matter how large, you can always construct a larger one. The Tower of Infinities rises without end. It doesn't just have two floors, countable and uncountable. It has infinitely many floors, and not just countably many floors. The tower itself is infinite in ways that transcend ordinary infinity. To understand this, we need to understand the concept of the power set. This is one of the most important constructions in all of mathematics, and it's the key to Cantor's infinite tower. Start with any set. It doesn't matter what the set contains. It could be a set of numbers, a set of people, a set of abstract mathematical objects. What matters is that it's a collection of things, and we can ask about its subsets. A subset is just a smaller collection drawn from the original. If your original set contains the numbers 1, 2, and 3, then some of its subsets are the set containing just 1, the set containing just 2, the set containing just 3, the set containing 1 and 2, the set containing 1 and 3, the set containing 2 and 3, and the set containing all 3. There's also the empty set, the set containing nothing at all. The empty set is technically a subset of every set, because it doesn't contain anything that isn't in the original. So for a set with 3 elements, we have 8 subsets in total. The power set is the set of all these subsets. It's a new set, larger than the original, whose elements are the subsets of the original. For finite sets, there's a precise relationship between the size of a set and the size of its power set. If a set has n elements, its power set has 2 to the power of n elements. A set with 1 element has 2 subsets, the empty set and the set itself. A set with 2 elements has 4 subsets. A set with 3 elements has 8 subsets. A set with 4 elements has 16 subsets. A set with 10 elements has 1024 subsets. The power set grows exponentially with the size of the original set. Even for modest sets, the power set becomes enormous. A set with just 20 elements has over 1 million subsets. A set with 30 elements has over 1 billion subsets. The power set dwarfs the original, and the larger the original, the more dramatic the dwarfing becomes. But what about infinite sets? What is the power set of an infinite set? This is where things become truly strange. Cantor proved that the power set of any infinite set is strictly larger than the original set. Not just larger in the vague sense of having more elements, larger in the precise sense that you cannot pair them up. There is no one-to-one correspondence between a set and its power set. No matter how cleverly you try to match elements with subsets, you will always fail. Some subsets will be left over. This is true for every set, finite or infinite. But for infinite sets, the implications are staggering. The proof uses an argument similar to the diagonal argument we saw earlier. Suppose you could pair up a set with its power set. then every element of the original set would correspond to exactly one subset, and every subset would correspond to exactly one element. Now consider the following subset. It contains all the elements that are not members of their corresponding subsets. Think about that carefully. An element X either belongs to its corresponding subset or it doesn't. We're collecting all the elements that don't belong to their corresponding subsets. This collection is itself a subset of the original set, so it should appear somewhere in the power set. Since we assumed we had a complete pairing, this subset must correspond to some element. Let's call that element Y. Now we ask, does Y belong to its corresponding subset? Remember, the corresponding subset of Y is precisely the set we constructed, the set of elements that don't belong to their corresponding subsets. If does belong to its corresponding subset, then by definition of how we constructed that subset, Y should not be in it. We only included elements that don't belong to their corresponding subsets. So if I is in, then Y shouldn't be in. Contradiction. If Y does not belong to its corresponding subset, then by definition, Y should be in it. We included all elements that don't belong to their corresponding subsets. So if it is out, then Y should be in. Contradiction again. Either way, we have a contradiction. Our assumption that we could pair the set with its power set must be false. No such pairing exists. The power set is strictly larger. This proof works for any set whatsoever. It doesn't matter whether the set is finite or infinite. It doesn't matter what the set contains. The power set is always larger, and this means there is no largest set. Given any set, take its power set. You get something larger. Take the power set of that. Something larger still. You can keep going forever, constructing larger and larger sets with no end in sight. The hierarchy of infinities doesn't stop at 2 levels. It doesn't stop at 3 levels, or 4, or 100, or 1,000,000. It goes on forever. There are infinitely many different sizes of infinity. Let's trace through the first few levels of this tower. At the bottom, we have the natural numbers, the counting numbers. Their cardinality is Aleph null, the smallest infinite cardinal. This is the ground floor of the infinite tower. One level up, we have the power set of the natural numbers. This is the set of all subsets of natural numbers. How many subsets are there? Well, the set of all even numbers is one subset. The set of all prime numbers is another. The set containing just the number 7 is another. The empty set is another. There are uncountably many subsets of natural numbers. The cardinality of this power set is 2 to the power of Aleph null. Cantor proved this equals the cardinality of the continuum, the cardinality of the real numbers. So the second floor of our tower is the continuum. But we don't have to stop there. We can take the power set of the real numbers. This is the set of all subsets of real numbers. How many such subsets are there? More than there are real numbers. The cardinality is 2 to the power of the continuum. This is an infinity larger than the continuum, larger than the reals, a third level of infinity that dwarfs everything below it. And we can take the power set again and again and again. Each time we ascend to a new level, we leave behind everything we knew before. Each new infinity is so much larger than the previous one that no pairing is possible. The gap between levels is absolute and unbridgeable. Let me try to give you some sense of how incomprehensibly large these infinities become. Consider the jump from the natural numbers to the real numbers. We've already seen that this is a qualitative leap, not just a quantitative increase. You cannot count the reals, you cannot list them. Any attempt to enumerate them leaves infinitely many behind. The infinity of reals is not just bigger than the infinity of naturals. It's a completely different kind of big. It's unreachable from below. Now consider the jump from the reals to the power set of the reals. This is another qualitative leap of the same magnitude. You cannot list all subsets of real numbers, not because there are a lot of them, but because the very concept of listing fails. The subsets are as far beyond the reals as the reals are beyond the naturals, and each subsequent level is another such leap. The tower rises through incomprehensibility after incomprehensibility, each flaw infinitely higher than the last. In our everyday experience, we sometimes encounter things that seem infinite. The number of grains of sand on all the beaches of Earth is enormous, roughly 7.5 quintillion, a 7 followed by 18 zeros, but this is finite. The number of atoms in the observable universe is estimated at about 10 to the 80th power, still finite. The number of possible chess games is staggeringly large, perhaps 10 to the 120th power, still finite. Even numbers like a Google, 10 to the 100th power, or a Googleplex, 10 to the Google power, are finite. They're inconceivably large by human standards, but they're still specific numbers, still countable in principle if you had unlimited time. The countable infinity is beyond all of these. It's not a large finite number, it's genuinely infinite, containing more elements than any finite number could count. And the uncountable infinity is beyond that. Not just more than countable, but qualitatively transcendent, unreachable by any counting process. And the infinity of subsets of reals is beyond that, and the next level beyond that, and so on forever. The human mind cannot truly grasp these magnitudes. We can prove theorems about them, we can establish their properties logically, but we cannot imagine them. They exceed our cognitive capacities by margins that themselves exceed comprehension. Cantor developed a notation for these infinite cardinals. He used Hebrew letters, Aleph followed by a subscript, to denote them. Aleph null was the smallest, the cardinality of the natural numbers. Aleph 1 was the next infinite cardinal, whatever that might be. Aleph 2 was the next, and so on. This raised an immediate question. We know the continuum, the cardinality of the reals, is bigger than Aleph null, but is it equal to Aleph 1? Is the continuum the next infinity after the countable? Or are there infinities in between? This is the continuum hypothesis, the question that tormented Cantor for decades. The continuum hypothesis states that there is no infinite set with cardinality between Aleph null and the continuum. The continuum is Aleph 1. It's the very next level up from the countable. There are no intermediate infinities, no half steps on the staircase, no levels between the ground floor and the first floor. This seems like it should be either true or false. Either there's an in-between infinity or there isn't. We should be able to prove it one way or the other. Cantor tried. He spent years trying. He convinced himself he had a proof, then found errors. He convinced himself again, found more errors. The problem consumed him, contributed to his mental breakdowns, haunted him to his grave. What he didn't know, couldn't have known, was that the continuum hypothesis is independent of standard mathematics. In 1940, the logician Kurt Gödel proved that you cannot disprove the continuum hypothesis using the standard axioms of set theory. If mathematics as we know it is consistent, then adding the continuum hypothesis doesn't create any contradictions. It might be true. In 1963, Paul Cohen proved the other direction. You cannot prove the continuum hypothesis either. If mathematics is consistent, then adding the negation of the continuum hypothesis also doesn't create contradictions. It might be false. Put these results together and you get something remarkable. The continuum hypothesis is undecidable. It's neither provable nor disprovable from the axioms we've accepted. It's a genuine gap in our mathematical knowledge, not because we haven't been clever enough to find a proof, but because no proof exists within the system. This was shocking. Mathematics was supposed to be the domain of certain knowledge, where every well-posed question had a definite answer, true or false, provable or disprovable. Gödel had already shaken this faith in 1931 with his incompleteness theorems, showing that any sufficiently powerful mathematical system contains statements that are true but unprovable within the system. But the continuum hypothesis felt different. It wasn't some obscure technical statement concocted specifically to demonstrate incompleteness. It was a natural question about the sizes of infinite sets, exactly the kind of question mathematics should be able to answer, and mathematics couldn't answer it. The question was too deep, or perhaps the axioms were too weak, or perhaps the very nature of mathematical truth was more complicated than anyone had imagined. Today, mathematicians are divided on what to think about the continuum hypothesis. Some believe it's true and that we should adopt axioms that imply it. Some believe it's false and favor different axioms. Some believe the question is genuinely meaningless, that there's no fact of the matter about whether intermediate infinities exist. And some believe we should simply accept the independence result and acknowledge that mathematics contains fundamental questions without answers. The debate continues, more than a century after Cantor first formulated the hypothesis, and there's no consensus in sight. What's certain is that Cantor opened a door that can never be closed. Before him, infinity was a vague notion, something mathematicians invoked when convenient but never examined too closely. After him, infinity became a precise mathematical concept, subject to rigorous analysis and yielding definite theorems. We know that some infinities are larger than others. We know the hierarchy extends forever. We know there are questions about infinity that mathematics cannot answer. These are permanent contributions to human knowledge, truths that will remain true as long as logic itself remains valid. Cantor paid a terrible price for these discoveries, enduring mockery, isolation, and mental illness. But the paradise he created, to use Hilbert's phrase, is now our permanent inheritance. Every mathematician who works with infinite sets, which is to say, virtually every mathematician, builds on foundations Cantor laid. His vision of infinity, strange and counterintuitive as it seemed to his contemporaries, became the standard picture of the infinite that we teach to students today. And yet, all of this remains in the realm of pure mathematics. Numbers and sets are abstract objects. They don't exist in space and time. They don't occupy volume or duration. The infinities Cantor studied are mathematical infinities, truths about the abstract realm of numbers. But what about the physical world? Is the universe infinite? Does space go on forever? Does time stretch endlessly into past and future? These are different questions. Questions about physical reality rather than mathematical abstraction. And as we'll see, they're just as strange, just as mind-bending, and even less certain than the mathematical puzzles Cantor solved. There is a question that almost everyone has asked at some point in their lives. Usually it happens in childhood. Lying on your back in the grass, staring up at the night sky, watching stars wheel slowly overhead. The question is simple. Does space go on forever? Is there an end to it somewhere? Some wall or boundary or edge beyond which there is nothing? Or does it extend without limit, galaxy after galaxy, void after void, stretching out in every direction forever? This is perhaps the most natural question a thinking being can ask about the cosmos. It's also one of the hardest to answer, and the answer, if we ever find it, has implications so profound that they touch on everything from the nature of existence to the possibility of other life to the ultimate fate of all matter and energy. When you look up at the night sky, you see points of light. Most of them are stars, distant suns, like our own, some larger, some smaller, some hotter, some cooler. The nearest star to our sun, Proxima Centauri, is about 4 light-years away. That means the light you see from it tonight left that star 4 years ago. It's been traveling through the void of space, crossing roughly 40 trillion kilometers just to reach your eye. And Proxima Centauri is close. It's our nearest neighbor. Most stars you can see with the naked eye are dozens or hundreds of light-years distant. Some are thousands. The light from those distant stars has been traveling since before you were born, before your grandparents were born, before entire civilizations rose and fell. When you look at the night sky, you're looking into the past, seeing light that left its source years or centuries or millennia ago. But the stars you can see are just the beginning. They're all part of our galaxy, the Milky Way, a vast spiral of stars rotating slowly around a central core. The Milky Way contains somewhere between 200 billion and 400 billion stars. That's a number so large that if you counted 1 star per second, it would take you thousands of years to finish. And yet the Milky Way is just one galaxy among many. In the early 20th century, astronomers weren't even sure other galaxies existed. They could see fuzzy patches of light in the sky, spiral shapes and elliptical blobs, but they didn't know if these were distant clouds of gas within our own galaxy or something else entirely. Separate island universes far beyond the Milky Way. In 1924, Edwin Hubble settled the question. Using the most powerful telescope of the time at Mount Wilson Observatory in California, he identified individual stars in the Andromeda Nebula. By measuring the brightness of certain types of stars whose intrinsic luminosity was known, he could calculate the distance. The result was staggering. Andromeda was not a nearby cloud. It was roughly 2 million light-years away, far beyond the boundaries of the Milky Way. It was a separate galaxy, comparable in size to our own, containing hundreds of billions of stars. And if Andromeda was a separate galaxy, then so were all those other fuzzy patches. The universe had suddenly grown by an almost unimaginable factor. We went from thinking the Milky Way was essentially everything to realizing it was just one island in an ocean of galaxies. Today we estimate that the observable universe contains roughly 2 trillion galaxies. That's 2,000 billion. Each galaxy contains billions or trillions of stars. The total number of stars in the observable universe is something like 200 sextillion, a 2 followed by 23 zeros, and each of those stars might have planets orbiting it. The sheer scale is beyond comprehension. The universe is not just big, it's not just enormous. It's so vast that every comparison fails, every analogy breaks down, every attempt to visualize it falls infinitely short. But here's the crucial point. Everything I've described so far is the observable universe. It's limited by the speed of light and the age of the cosmos. Light has been traveling toward us since the Big Bang, roughly 13.8 billion years ago. But it can only have traveled so far in that time. Light from objects beyond a certain distance hasn't had time to reach us yet. We can't see those objects. We don't know they're there. They're beyond our cosmic horizon. The observable universe has a radius of about 46 billion light-years. This is larger than 13.8 billion because space itself has been expanding while the light traveled. But it's still finite. It's a sphere centered on Earth, containing everything we can possibly observe. Beyond that sphere, there's more universe, but we can't see it. We might never see it. So how big is the whole universe, including the parts we can't observe? This is where things get deeply uncertain. The honest answer is that we don't know. We might never know. The universe beyond our cosmic horizon might be finite, extending for some distance and then stopping, or it might be infinite, going on forever in every direction, with no edge, no boundary, no end. Current evidence is maddeningly ambiguous. One approach is to measure the geometry of space. Einstein's theory of general relativity tells us that the shape of space depends on the amount of matter and energy it contains. If there's more than a critical amount, space curves back on itself like the surface of a sphere. In such a universe, if you traveled far enough in one direction, you'd eventually return to your starting point, like circumnavigating the Earth. The universe would be finite, but without an edge. There's no wall you'd run into, no boundary you'd cross. You'd just keep going and eventually come back to where you started. If there's less than the critical amount of matter and energy, space curves the other way, like a saddle. Such a universe would be infinite, stretching out forever, with parallel lines eventually diverging. And if there's exactly the critical amount, space is flat. Parallel lines stay parallel forever. The geometry is Euclidean, the kind you learned in school. A flat universe could be infinite, like an endless plane, or it could be finite with a strange topology, like a video game screen, where going off one edge brings you back on the opposite side. We've measured the curvature of space using the cosmic microwave background, the afterglow of the Big Bang that fills all of space with faint radiation. The measurements are extraordinarily precise, and the result is that space is flat, or very nearly so. Within our measurement uncertainty, the curvature is zero. This is consistent with an infinite universe, but it doesn't prove it. A very large finite universe would also appear flat at the scales we can measure, just as the Earth's surface appears flat when you're standing on it, even though it's actually curved. The flatness measurement tells us the universe is at least very large, much larger than the observable portion. But it doesn't tell us whether it's infinite. There's another way to think about this question. In the standard cosmological model, the universe began with the Big Bang roughly 13.8 billion years ago. Space, time, matter, and energy all emerged from that initial event. But what triggered the Big Bang? The leading theory is called cosmic inflation. It proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion. Space itself stretched by an enormous factor, possibly by more than a factor of 10 to the 26th power in a tiny fraction of a second. This inflation smoothed out irregularities, flattened the curvature of space, and set the stage for the universe we observe today. But inflation has a strange consequence. In most versions of the theory, inflation doesn't end everywhere at the same time. It ends in some regions, allowing normal expansion to take over, but continues in others. The regions where inflation ends become pocket universes like ours. But the regions where inflation continues keep expanding exponentially, spawning more pocket universes, which spawn more forever. This is called eternal inflation. If it's correct, then our observable universe is just one bubble in an infinite sea of bubbles. An infinite number of other universes exist beyond our cosmic horizon, forever out of reach, forever unobservable. The multiverse, as it's called, would be genuinely infinite, containing infinitely many regions like our own, plus infinitely many regions that might have different physical laws, different constants, different properties altogether. This is speculative. We have no direct evidence for eternal inflation or the multiverse. We might never have such evidence, since these other regions are beyond our cosmic horizon and can't send us signals. Some physicists embrace the multiverse as a natural consequence of our best theories. Others dismiss it as unscientific, since we can't test it. The debate is ongoing and sometimes heated, but it illustrates how infinity keeps cropping up in our theories of the cosmos. We can't seem to avoid it. Every time we push our understanding further, infinity seems to be lurking at the edges, hinting that reality might be far larger than we can observe. Let's suppose, for the sake of argument, that space is genuinely infinite. What would that mean? The implications are almost too strange to contemplate. In an infinite universe with a roughly uniform distribution of matter, everything that can happen does happen. Not once, but infinitely many times. This includes you. Think about it. You are a particular arrangement of atoms. Roughly 7 octillion atoms, give or take, organized into cells and tissues and organs and a brain that somehow produces consciousness. There are only finitely many ways to arrange that many atoms. The number is enormous, far larger than any number we've discussed, but it's still finite. In an infinite universe, every possible arrangement of atoms occurs somewhere, including the arrangement that constitutes you. This means there would be infinitely many copies of you out there, scattered through infinite space. Some of these copies would be exactly identical, living lives exactly like yours, reading these exact words at this exact moment. Others would be almost identical, differing in some small detail, perhaps wearing a different shirt, perhaps having made a different choice at some point in the past. Still others would be more different, sharing your DNA, but having lived very different lives. And all of them would exist, really and truly, just inconceivably far away. This isn't science fiction, it's a logical consequence of infinite space. If space goes on forever, and matter is distributed throughout it, then given enough distance, every possible configuration of matter occurs. You are not unique. You are one of infinitely many. Your experiences, your thoughts, your choices, all are replicated infinitely throughout the cosmos. Does this thought comfort you or disturb you? For some people, it's deeply unsettling. Our sense of identity seems to depend on our uniqueness. I am me, not someone else. My experiences are mine, not copies of someone else's experiences. But if there are infinitely many yous, what does identity even mean? How can you be special if there are infinitely many beings exactly like you? For other people, There's something liberating about this idea. Every possibility is realized. Every choice you didn't make, some other version of you did make. Every path not taken is taken somewhere. The universe contains all possibilities, not just the ones that happen to occur in your particular corner of it. But let's step back from speculation and return to what we can actually observe. The observable universe, the part we can see, is finite. It has a specific size, a specific number of galaxies, a specific amount of matter. Whether the universe beyond is finite or infinite, the observable portion is our home, the arena in which all of human history has occurred and all of human future will unfold. And even this finite portion is so vast that we can barely comprehend it. The light from distant galaxies has been traveling for billions of years to reach us. We see those galaxies as they were billions of years ago, when the universe was young, when the first stars were forming, when the cosmos looked very different from how it looks today. We are seeing into the past, glimpsing the history of the universe, reading the story of cosmic evolution written in light. The expansion of the universe adds another layer of strangeness. Space itself is stretching, carrying galaxies along with it. Nearby galaxies are moving away from us slowly. Distant galaxies are moving away faster. The most distant galaxies we can observe are receding at speeds approaching the speed of light. And beyond our cosmic horizon, there are regions of space receding faster than light. This doesn't violate relativity, because it's space itself that's expanding, not objects moving through space. But it means those regions are forever out of reach. Light from them will never reach us. No matter how long we wait, they are causally disconnected from us, as unreachable as if they didn't exist at all. The far future of the universe is shaped by this expansion. Current evidence suggests the expansion is accelerating, driven by a mysterious something called dark energy. We don't know what dark energy is. We don't know why it exists, but we can measure its effects. It's pushing galaxies apart faster and faster. If this continues, and we have no reason to think it won't, the universe will become increasingly lonely over time. Distant galaxies will recede beyond our cosmic horizon, one by one, becoming unobservable. In the far future, trillions of years from now, the night sky will be dark. Our local group of galaxies will have merged into a single giant galaxy, but everything else will have vanished beyond the horizon. Future astronomers, if any exist, will see only their own galaxy, surrounded by blackness. They might not even know the universe was ever different. They might conclude they live in a small, finite cosmos, never suspecting the billions of galaxies that once filled the sky. And even further into the future, that final galaxy will die. Stars will burn out. Black holes will evaporate. Matter itself might decay into radiation. The universe will approach a state of maximum entropy. A cold, dark, changeless void. Time will continue, perhaps forever, but nothing will happen. No events, no changes, no observers, just endless emptiness stretching into eternity. This is called the heat death of the universe. It's the most likely ultimate fate of the cosmos, given what we currently know. An infinite future of nothing. Is this depressing? Perhaps, but there's something majestic about it too. We exist at a special time, a brief window in cosmic history, when the universe is active and interesting, when stars shine and galaxies swirl and life can exist. The universe was not always this way. It will not always be this way. But right now, in this moment, there is light and warmth and complexity and consciousness. We are here, thinking about infinity, contemplating the cosmos, asking questions about the nature of existence. That's remarkable. That's precious. Against the backdrop of an infinite and mostly empty universe, our existence is a tiny flame. But a flame, however small, is still a light in the darkness. The question of whether the universe is spatially infinite remains open. We don't know the answer. We might never know. The universe might extend forever, containing infinite matter, infinite galaxies, infinite copies of everything that exists. Or it might be finite, a vast but bounded region of space, possibly curving back on itself, possibly embedded in something larger we can't comprehend. Either answer is consistent with current observations. Either answer raises profound questions. Infinity in space is not a settled matter. It's a mystery, a frontier, a question that humanity has asked for millennia and still cannot answer with certainty. But one thing is clear: whether the universe is finite or infinite, it is immense, beyond human comprehension. It dwarfs everything we know, everything we can imagine, everything we will ever experience. The distances are too large, the numbers too vast, the timescales too long for our evolved brains to truly grasp. We evolved to navigate African savannas, to track prey, to avoid predators, to recognize faces and count small numbers. We did not evolve to comprehend billions of light years or trillions of galaxies or timescales of billions of years. When we contemplate the cosmos, we are pushing our cognitive equipment far beyond its design specifications. We can do the mathematics, we can write down the numbers, but we cannot feel them in our bones. The universe is too big for us. We can know this intellectually, but we cannot truly understand it viscerally. And perhaps that's okay. Perhaps the universe's vastness is not a challenge to be overcome, but a mystery to be appreciated. We are small creatures in an immense cosmos. And somehow, against all odds, we have figured out just how immense it is. That's not a failure of comprehension, that's a triumph of it. We've explored infinity in numbers, in the abstract realm of mathematics, where Cantor built his tower of ever larger infinities. We've explored infinity in space, asking whether the universe extends forever in every direction. But there's another dimension to consider, one that touches our lives more intimately than any mathematical abstraction or cosmological speculation. Time. Does time go on forever? Did it have a beginning? Will it have an end? And what would it mean to exist eternally, to experience infinite duration? These questions have haunted humanity since we first became capable of contemplating our own mortality. They're not just abstract puzzles. They're deeply personal, connected to our hopes and fears, our religious traditions, our understanding of what it means to be alive. Think about the past. Right now, at this moment, you exist. You're reading these words, thinking these thoughts, experiencing this present instant. But there were moments before this one. An hour ago, you were doing something else. A day ago, something else still. A year ago, a decade ago, a century ago before you were born, a millennium ago, 10,000 years ago, a million years ago. The past stretches back behind us, a chain of moments extending into the depths of time. How far does it go? Was there a first moment, a beginning, before which there was nothing? Or does the past extend infinitely, with no start, no origin, no first instant from which everything else followed? For most of human history, different cultures gave different answers to this question. Many creation myths describe a beginning. In the beginning, God created the heavens and the earth. Before that, there was nothing, or chaos, or a primordial void. Time itself began with creation. There was no before, because before implies time, and time didn't exist yet. This view places a definite starting point on the past. Time is finite in the backward direction. It had a beginning, even if that beginning is shrouded in mystery or miracle. Other traditions imagine time as cyclical, endlessly repeating. The universe goes through phases of creation and destruction, birth and death, expansion and contraction. Each cycle might be finite, but the cycles repeat forever. There's no ultimate beginning because every beginning is preceded by the end of a previous cycle. In this view, time is infinite in a strange way, not a line stretching back forever, but a circle turning endlessly. Modern cosmology gives us a specific picture of the past. The universe as we know it began with the Big Bang, roughly 13.8 billion years ago. At that moment, space and time as we understand them came into existence. The universe was unimaginably hot and dense, a seething plasma of fundamental particles and radiation. It expanded and cooled, forming atoms, then stars, then galaxies, then planets, and eventually, on at least one planet, life and consciousness. This is the story told by our best physical theories, supported by multiple lines of evidence, from the cosmic microwave background to the abundance of light elements to the observed expansion of space. But was the Big Bang truly the beginning of time? This is more subtle than it might seem. Our current physical theories break down at the moment of the Big Bang itself. The equations of general relativity, which describe gravity and the structure of space-time, produce infinities when you try to apply them to the initial instant. Infinite density, infinite temperature, infinite curvature. These infinities are signals that the theory has reached its limits, that it's no longer giving us reliable answers. We need a theory of quantum gravity, a framework that combines general relativity with quantum mechanics to understand what really happened at the very beginning. And we don't have such a theory yet. We have candidates, like string theory and loop quantum gravity, but none of them are complete, and none of them have been experimentally tested. Some of these candidate theories suggest that the Big Bang was not the absolute beginning. Perhaps our universe emerged from a previous universe that collapsed in a big crunch. Perhaps it budded off from a parent universe in some process we don't yet understand. Perhaps time extends infinitely into the past, with the Big Bang being just one event in an eternal cosmic history, not the first event. We simply don't know. The question of whether time had a beginning remains open, one of the deepest unsolved problems in physics. The past might be finite, starting at the Big Bang or something like it, or the past might be infinite, extending forever with no starting point. Our current knowledge doesn't decide between these possibilities. The philosopher Augustine of Hippo wrestled with this question 16 centuries ago. In his Confessions, written around 400 CE, he asked what God was doing before creating the universe. If God existed before creation, what was he doing during all that infinite time? Why did he wait so long to create? Augustine's answer was radical and surprisingly modern. He argued that time itself was created along with the universe. There was no before the creation, because before implies time, and time didn't exist until God made it. The question of what God was doing before creation is meaningless, like asking what's north of the North Pole. The very concept of before doesn't apply. This idea that time might have a beginning, that there might be no before the first moment, is strange to contemplate. Our everyday experience tells us that every moment is preceded by another moment. Every now comes after a then. The very grammar of our language encodes the assumption that time flows continuously from past to present to future. To imagine a first moment, a beginning with nothing before it, seems almost contradictory. What made that moment happen? What caused the universe to begin? These questions seem to demand answers. But if there was no time before the beginning, the questions might not even make sense. Now let's turn to the future. If the past might have a beginning, does the future have an end? Will there be a last moment, a final instant, after which nothing happens? Or does the future extend forever, an infinite succession of moments stretching ahead without limit? Here the scientific picture is clearer, at least in broad outline. According to our current understanding, the universe will continue existing for an extremely long time, far longer than it has existed so far. But continue existing doesn't mean continue being interesting. The far future of the universe is a story of slow decay. Stars are burning through their nuclear fuel, converting hydrogen to helium, to heavier elements, releasing energy that lights up the cosmos. But the fuel is finite. Stars will burn out. The most massive stars have already died, exploding as supernovae after just a few million years. Medium-sized stars like our Sun have longer lifetimes, about 10 billion years total, of which about 5 billion have already passed. The smallest stars, red dwarfs, burn so slowly that they can last for trillions of years. But even they will eventually exhaust their fuel and fade away. In the far future, perhaps 100 trillion years from now, the last stars will have burned out. The universe will be dark, lit only by the faint glow of white dwarfs slowly cooling, neutron stars gradually spinning down, black holes silently lurking in the void. This is the degenerate era, a time when no new stars form because all the hydrogen has been used up and the old stars have all died. The universe will be cold and dark and mostly empty. But it won't be over. Time will continue. Things will still happen, just very slowly. Black holes will dominate this era, They're the most stable objects in the universe, lasting far longer than stars. But even black holes aren't eternal. Through a process called Hawking radiation, discovered by physicist Stephen Hawking in 1974, black holes slowly evaporate. They emit particles, losing mass in the process, gradually shrinking until they finally wink out of existence in a final burst of radiation. This process is incredibly slow. A black hole with the mass of the Sun would take about 10 to the 67th power years to evaporate. That's a 1 followed by 67 zeros, a number so large that comparing it to the current age of the universe is like comparing the age of the universe to a single instant. But eventually, given enough time, all black holes will evaporate. The universe will enter a new era, sometimes called the dark era. There will be nothing left but scattered particles, photons, and possibly the decay products of protons, if protons themselves are unstable, which some theories suggest. The universe will approach a state of maximum entropy, a condition where energy is spread out as evenly as possible and no useful work can be done. This is the heat death of the universe, predicted by thermodynamics in the 19th century, and still our best guess for the ultimate fate of the cosmos. In the heat death scenario, time continues forever. There's no final moment, no last instant, no end to the sequence of moments. But nothing happens. The universe has reached equilibrium. It's not dead in the sense of having stopped existing. It's dead in the sense of having stopped changing. Every part of the universe is the same temperature, the same density, the same level of chaos. There are no gradients, no differences, nothing to drive any process or change. Time passes, but the passage of time accomplishes nothing. Eternity stretches ahead, but it's an eternity of sameness, of stasis, of cold, dark emptiness. Is this truly infinite time? In one sense, yes. The sequence of moments continues without end. There is no last moment. You can always ask what happens next, and the answer is more of the same, forever. But in another sense, it's not the infinity we usually imagine when we think about eternity. It's not an infinity of experiences, of events, of happenings. It's an infinity of nothing, an endless expanse of timeless time, duration without content, existence without life. This raises a profound philosophical question. What would it mean to live forever? To experience infinite time? We often think of immortality as desirable. Death is frightening, final, an end to everything we know and love. Wouldn't it be wonderful to escape it, to live on indefinitely, to have unlimited time for everything we want to do? Religions promise eternal life as the ultimate reward. Transhumanists dream of technological immortality, of uploading minds into computers or rejuvenating bodies indefinitely. The desire to escape death is one of the deepest human impulses, but think carefully about what eternal life would actually involve. You would experience moment after moment, day after day, year after year, century after century, millennium after millennium. The experiences would accumulate without limit. At first, this might seem wonderful. So much to see, so much to learn, so much to do. But eventually, after millions or billions of years, would you run out of new experiences? There are only finitely many books, finitely many places to visit, finitely many people to meet, finitely many thoughts to think. The number is enormous, but it's still finite. In infinite time, you would eventually exhaust every possibility. You would have read every book, visited every place, met every type of person, thought every thought. What then? The philosopher Bernard Williams argued that immortality would be unendurable. After you've done everything, what's left? Boredom, stretching on forever, repetition, doing the same things again and again, because there's nothing new. Your personality might dissolve as experiences pile up beyond all recognition, as memories blur together into an indistinguishable mass, as the you of year 1,000,000 becomes utterly disconnected from the you of year 1. Williams suggested that death, far from being a tragedy, might be a gift. It gives life urgency. It makes things matter. Without death, nothing would be special, because you could always do it later. With infinite time, there's no reason to do anything now. There's no now that's more important than any other now. The Argentine writer Jorge Luis Borges explored this idea in his short story The Immortal. In the story, a Roman soldier discovers a race of immortals who have lived for thousands of years. But instead of being wise and accomplished, they've become passive and indifferent. They've stopped building, stopped creating, stopped caring. They've done everything, seen everything, felt everything. Nothing moves them anymore. They sit in silence, barely acknowledging each other, waiting for nothing because there's nothing left to wait for. Borges suggests that meaning requires limitation. We care about things because they're fleeting, because they won't last, because there's only so much time and we have to choose how to spend it. Remove the limitation and meaning drains away. But perhaps this is too pessimistic. Perhaps an immortal mind could find ways to remain engaged forever. Perhaps new experiences could be generated indefinitely. New thoughts, new joys discovered. Perhaps consciousness itself could evolve and expand, finding depths of experience that we finite beings can't even imagine. We don't really know what eternal existence would be like because we have no experience of it. Our intuitions about infinite time are shaped by our finite lives, and those intuitions might not apply. The question remains genuinely open. There's also the question of personal identity over infinite time. If you live for billions of years, changing and growing and accumulating experiences, in what sense are you still the same person who started the journey? The you of year 1 billion might have almost nothing in common with the you of year 1. Different memories, different values, different personality, different everything. The continuity of identity that makes us feel like coherent selves might not survive infinite duration. You might become a succession of different people, connected by causal chains, but not by any deeper unity. Living forever might not mean you live forever. It might mean that a series of increasingly different beings exists, each one connected to the previous one, but none of them really being you in any meaningful sense. These are not just idle speculations. As biotechnology advances, as medicine extends lifespans, as some people seriously contemplate radical life extension, these questions become more pressing. What are we hoping for when we hope for immortality? What would we actually get? Would eternal life be a blessing or a curse? The infinity of time confronts us with these questions, forcing us to think about what we value, what makes life meaningful, and what we really want when we say we want more time. The past might be finite, beginning at some first moment. The future might be infinite, stretching on forever without end. But infinite future time might not be the gift we imagine. It might be an empty eternity, a cosmos running down to stillness, a fate that makes our brief spark of existence all the more precious by contrast. We live in a window, a brief interval when the universe is active and interesting, when stars shine and life flourishes and minds contemplate infinity. Before this window, perhaps nothing. After this window, perhaps nothing meaningful. But right now, in this moment, we exist. And that existence, however brief, is something rather than nothing. It's a candle flame in the void, a temporary structure amid eternal chaos, a miracle of complexity in a universe tending towards simplicity. Maybe that's enough. Maybe that's more than enough. Maybe the infinity of time, with all its terrors and wonders, only makes the present moment more worth cherishing. We've explored infinity in mathematics, in space, in time. We've seen how it breaks our intuitions, defies our expectations, and reveals depths of strangeness that our minds can barely grasp. But we haven't yet visited the most famous playground of infinity, the thought experiment that captures more of infinity's paradoxes in a single image than anything else ever devised. I'm talking about Hilbert's Hotel. If you want to understand why infinity is truly, fundamentally different from any finite quantity, no matter how large, Hilbert's Hotel is where you need to stay. But be warned, once you check in, you might never see mathematics the same way again. David Hilbert was one of the greatest mathematicians of the 20th century. Born in 1862 in Königsberg, Prussia, he made fundamental contributions to nearly every branch of mathematics: algebra, number theory, geometry, analysis, mathematical physics, and the foundations of mathematics itself. He was a contemporary of Cantor, and unlike many of their colleagues, Hilbert recognized the importance and validity of Cantor's work on infinity. It was Hilbert who declared that no one would expel us from the paradise that Cantor created. He championed set theory when others attacked it, defended the legitimacy of infinite mathematics, and helped establish it as the foundation of modern mathematical practice. But Hilbert also had a gift for exposition, for finding vivid examples that made abstract ideas concrete. And his most famous example, conceived sometime in the early 20th century, was the Grand Hotel. "Imagine a hotel," Hilbert said, "but not an ordinary hotel. This hotel has infinitely many rooms. Room 1, room 2, room 3, room 4, and so on forever. There is no last room. No matter how high you count, there's always another room with a higher number. The hotel stretches on forever. Corridor after corridor, floor after floor, an endless array of rooms extending to infinity. Now imagine that the hotel is completely full. Every single room is occupied. Room 1 has a guest. Room 2 has a guest. Room 3, room 4, room 5, all occupied. Every room, all infinitely many of them, has exactly one guest staying in it. The hotel is at maximum capacity. No vacancies. The no vacancy sign is lit up outside. A new guest arrives at the front desk. They'd like a room for the night. In any ordinary hotel, the answer would be simple. Sorry, we're fully booked. Try another hotel. There are no empty rooms. We can't accommodate you. But this is not an ordinary hotel. This is the Grand Hotel with infinitely many rooms. And in this hotel, even when every room is occupied, there's still room for one more. Here's what the manager does. They ask the guest in room 1 to move to room 2. The guest in room 2 moves to room 3. The guest in room 3 moves to room 4. Every guest moves from their current room to the room with the next higher number. The guest in room N moves to room N+1. This works for every guest, no matter how high their room number. Room 1 million, move to room 1 million and 1. Room 1 trillion, move to room 1 trillion and 1. Every guest can move because every guest has a room with a higher number to move into. When all the moves are complete, something remarkable has happened. Every original guest still has a room. No one has been kicked out. The guest who was in room 1 is now in room 2. The guest who was in room 2 is now in room 3. Everyone has simply shifted down the corridor by one room. But now room 1 is empty. The first room has no occupant because everyone moved up. The new guest can check into room 1. The hotel was completely full, and yet it accommodated an additional guest without removing anyone. This seems impossible. It seems like a violation of basic logic. If every room is occupied, how can there be room for someone new? In any finite hotel, this would be impossible. If you have 100 rooms and 100 guests, there's no way to fit 101st guest without kicking someone out. But infinity doesn't work like finite numbers. An infinite hotel can accommodate one more guest even when full because infinity plus 1 equals infinity. You're not making the hotel bigger, you're just rearranging the guests. And in an infinite hotel, there's always room to rearrange. But Hilbert didn't stop there. The paradoxes were just beginning. Suppose a bus arrives at the hotel. Not an ordinary bus, but a bus carrying 50 new guests. The hotel is still completely full from before, all infinitely many rooms occupied. Can the manager accommodate 50 new guests? Easily. Ask every current guest to move from room N to room N+50. The guest in room 1 moves to room 51. The guest in room 2 moves to room 52. The guest in room 50 moves to room 100. Everyone shifts up by 50 rooms. Now rooms 1 through 50 are empty, ready for the 50 new guests. Once again, no one was kicked out, everyone still has a room, and the hotel absorbed 50 additional guests while supposedly being completely full. The same trick works for any finite number of new guests. 1,000 new guests arrive, shift everyone up by 1,000. 1,000,000? Shift by 1,000,000. It doesn't matter how many finite guests arrive, The infinite hotel can always accommodate them by shifting the existing guests up by that amount. Infinity plus any finite number equals infinity. The hotel absorbs new guests without growing because it was already infinitely large. There's always room to rearrange. Now comes the truly mind-bending part. Suppose an infinitely long bus arrives. This bus has infinitely many passengers. Passenger 1, passenger 2, passenger 3, and so on forever. Infinitely many new guests, each wanting a room. The hotel is already full with infinitely many guests. Can the manager accommodate infinitely many new guests? It seems like this should be impossible. You already have infinity guests. You're adding infinity more. Surely now you've exceeded the hotel's capacity. Surely now there aren't enough rooms. But the manager has another trick. Instead of shifting guests by a finite amount, shift them to different positions entirely. Ask every current guest to move from room N to room 2N. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6. The guest in room 4 moves to room 8. Every guest moves from their odd-numbered room to an even-numbered room with twice the number. When the dust settles, look at what's happened. Every original guest is now in an even-numbered room, room 2, room 4, room 6, room 8. All the even rooms are occupied. But what about the odd rooms? Room 1 is empty. Room 3 is empty. Room 5 is empty. Room 7 is empty. All the odd-numbered rooms are vacant, and there are infinitely many odd numbers. There are infinitely many empty rooms now, one for each new guest from the infinite bus. The infinite bus passengers check in. Passenger 1 goes to room 1. Passenger 2 goes to room 3. Passenger 3 goes to room 5. Passenger 2 goes to room 2. N-1, the nth odd number. Every passenger gets a room. Every original guest still has a room. The hotel accommodated infinitely many new guests without removing anyone. The occupancy has doubled, but the hotel hasn't grown because it was already infinite. Two infinities fit into one infinity with room to spare. This is what Cantor proved about the natural numbers and the even numbers. There are just as many even numbers as natural numbers because you can pair them up perfectly. In Hilbert's hotel, this abstract mathematical fact becomes a concrete image. You see the pairing happening. You watch the guests move. The impossibility of infinity becomes, if not intuitive, at least visible. But wait, the paradoxes go deeper still. Suppose infinitely many buses arrive, each carrying infinitely many passengers. Bus 1 has passengers 1, 2, 3, 4, and so on. Bus 2 also has passengers 1, 2, 3, 4, and so on. Bus 3, the same, infinitely many buses, each with infinitely many passengers. Infinity times infinity guests. Can the hotel accommodate them all? Incredibly, yes, the manager needs a more sophisticated arrangement, but it can be done. One approach uses prime numbers. Every integer greater than 1 can be uniquely expressed as a product of prime numbers. 2, 3, 5, 7, 11, 13, and so on. This is the fundamental theorem of arithmetic. The manager can use this to assign rooms. The current guests, who are already in the hotel, get moved to powers of 2. The guest in room 1 moves to room 2 to the first power, which is 2. The guest in room 2 moves to room 2 squared, which is 4. The guest in room 3 moves to room 2 cubed, which is 8. The guest in room N moves to room 2 to the N. Every current guest gets a unique room because every power of 2 is different. Passengers from bus 1 get moved to powers of 3. Passenger 1 from bus 1 goes to room 3. Passenger 2 from bus 1 goes to room 9. Passenger 2 from bus 1 goes to room 3. To the N, passengers from bus 2 get powers of 5. Passenger 1 from bus 2 goes to room 5. Passenger 2 goes to room 25. Passenger N goes to room 5 to the N. Passengers from bus 3 get powers of 7. Bus 4 gets powers of 11. Bus 5 gets powers of 13. Each bus is assigned a different prime number, and passengers from that bus get powers of that prime. Because every number has a unique prime factorization, no two guests ever end up in the same room. The guest in room 6, which is 2 times 3, isn't any of our assigned guests, because 6 isn't a pure power of any prime. Room 6 stays empty, as do many other rooms, but that's fine. We have infinitely many rooms. We can afford to leave some empty. The important thing is that every guest, from every bus, has a unique room. Infinity times infinity guests fit into the infinite hotel. This corresponds to Cantor's proof that the rational numbers are countable. The fractions can be arranged in a grid, like passengers on buses, and then enumerated with a clever diagonal argument. Infinitely many rows, infinitely many columns, yet still countable, still the same size as the natural numbers. Hilbert's Hotel makes this abstract fact tangible. But now let's consider what happens when guests check out. The hotel is full. Infinitely many guests in infinitely many rooms. Suppose the guest in room 1 checks out. Now room 1 is empty. Easy to understand. 1 guest left, 1 room empty. Infinity minus 1 equals infinity minus 1, which is still infinity. The hotel is still essentially full. Suppose all the guests in odd-numbered rooms check out. Room 1, room 3, room 5, room 7. All the odd rooms are now empty. Infinitely many guests have left, but infinitely many remain. In all the even-numbered rooms, we started with infinity, subtracted infinity, the odd room guests, and we're left with infinity, the even room guests. Infinity minus infinity equals infinity. Sort of. But what kind of infinity? We have the same number of guests as before, just fewer rooms occupied. The remaining guests can shift down, moving from room 2 nan to room n, and fill the hotel completely again. The mathematics works out consistently, but here's where things get strange. Suppose instead that all guests in rooms numbered greater than 100 check out. Room 101, room 102, room 103, all empty. Infinitely many guests have left, but only 100 remain. In rooms 1 through 100, we started with infinity, subtracted infinity, and got 100. Infinity minus infinity equals 100. Or suppose everyone checks out. Every single guest leaves. We started with infinity, subtracted infinity, and got 0. Infinity minus infinity equals 0. Do you see the problem? Infinity minus infinity doesn't have a single answer. It depends on which infinity you subtract. If you remove the odd-numbered guests, you're left with infinitely many. If you remove everyone except the first 100, you're left with 100. If you remove everyone, you're left with 0. The same operation, infinity minus infinity, gives different results depending on how you perform it. This is why mathematicians say that infinity minus infinity is undefined. It's not that we don't know the answer, it's that there is no single answer. The expression is ambiguous. It could equal anything from 0 to infinity, depending on the specific infinities involved. This is fundamentally different from ordinary arithmetic, where subtraction always gives a unique answer. 5 minus 3 is always 2, no matter how you subtract. But infinity minus infinity could be anything. This has profound implications. It means you can't treat infinity like a number. You can't do arithmetic with it in the normal way. The rules that work for finite numbers break down completely when infinity enters the picture. Infinity plus 1 equals infinity. Infinity times 2 equals infinity. Infinity plus infinity equals infinity. But infinity minus infinity is undefined, meaningless, a question that doesn't have an answer. Hilbert's Hotel captures all of this in a single, unforgettable image. The infinite hotel, always full, yet always able to accommodate more guests. The endless shifting of rooms, the impossibility that becomes routine, the arithmetic that defies common sense. It's a playground where the normal rules don't apply, where the impossible happens every day, where infinity reveals its true nature as something utterly unlike any finite quantity. Some people find Hilbert's Hotel disturbing. It seems to violate logic, to prove that mathematics is contradictory, to show that infinity leads to absurdity. But mathematicians don't see it that way. They see Hilbert's Hotel as a demonstration of how infinity actually works. The results seem paradoxical only because our intuitions are trained on finite numbers. We expect the rules for finite arithmetic to apply universally, but they don't. Infinity has its own rules, consistent and coherent once you understand them, but radically different from anything in our everyday experience. The hotel is just a thought experiment, of course. You can't actually build an infinite hotel. But the mathematics it illustrates is real. Infinite sets behave in exactly these counterintuitive ways. The natural numbers can be put in one-to-one correspondence with the even numbers, with the perfect squares, with the rational numbers. You can add infinitely many elements to an infinite set without changing its cardinality. You can remove infinitely many elements and get different results depending on which elements you remove. These are proven mathematical facts, established with rigorous logic, not speculation or hand-waving. When you truly absorb what Hilbert's Hotel teaches, you realize that infinity is not just a very large number. It's a different kind of thing entirely. Large numbers, no matter how large, still obey the ordinary rules of arithmetic. A Google plus 1 is bigger than a Google. A Googleplex minus a Google is less than a Googleplex. But infinity doesn't work this way. Infinity plus 1 is the same as infinity. Infinity minus infinity is undefined. The usual operations don't apply, or they apply in strange new ways that violate our expectations. This is what the ancients feared. This is why Aristotle distinguished potential from actual infinity and rejected the latter. This is why mathematicians for 2,000 years treated infinity gingerly, using it when necessary, but never examining it too closely. They sensed that infinity contained contradictions, paradoxes, results that seemed to undermine the foundations of logic itself, and they were right to be cautious. But they were wrong to conclude that infinity was incoherent. Infinity is strange. Yes, counterintuitive, absolutely, but not contradictory. The mathematics of infinity, developed by Cantor and others, is perfectly consistent. It just requires us to abandon our finite intuitions and accept that the infinite follows different rules. Hilbert's Hotel is a gateway to this understanding. When you check in, you leave the familiar world of finite arithmetic behind. You enter a realm where the impossible is routine, where paradox is proof, where the rules you learned in school no longer apply. It's disorienting at first. It might even feel threatening, as if the ground beneath mathematics is shifting. But once you adjust, once you accept infinity on its own terms, a vast new landscape opens up. A landscape of different-sized infinities, of hierarchies extending forever upward, of questions that mathematics itself cannot answer. The infinite hotel is just the beginning. Beyond it lies a universe of mathematical structure more complex and beautiful than anything finite could contain. Check out of Hilbert's Hotel and you return to the finite world, to everyday arithmetic, to the comfortable rules you've always known, but you carry something with you. A knowledge that those rules are not universal, a sense of the vast strangeness waiting just beyond the familiar. Infinity is out there, and it plays by its own rules. Hilbert's Hotel showed you what those rules look like. You can never forget it. You can never see mathematics quite the same way again. We've spent most of our journey exploring infinity in the realm of pure mathematics. Numbers and sets, hierarchies and cardinalities, abstract structures that exist in some Platonic realm of pure thought. Mathematicians study infinity. They classify it, prove theorems about it, build elaborate theories to capture its properties. For mathematicians, infinity is an object of study, something to be understood and mastered. But for physicists, infinity is something very different. For physicists, infinity is usually a sign that something has gone terribly wrong. When infinity appears in a physics equation, it doesn't mean you've discovered something deep about the universe. It means your theory has broken down. It means you've pushed your equations beyond their domain of validity. It means you've asked a question that your theory cannot answer. Physicists have a word for these infinities: singularities. And singularities are not triumphs of understanding. They are confessions of ignorance. They are places where our knowledge runs out, where our equations fail, where the map no longer matches the territory. Understanding how infinity haunts physics and how physicists have learned to work around it, reveals something profound about the relationship between mathematics and physical reality. Let's start with the simplest infinity in physics: division by zero. You learned in school that you cannot divide by zero. The operation is undefined, but why? What happens when you try? Consider the expression 1 divided by x, where x is some number. When x is large, the result is small. 1 divided by 10 is 1/10. 1 divided by 100 is 1/100th. 1 divided by 1,000,000 is 1/1,000,000th. As x gets larger, the result gets smaller, approaching zero. Now go the other direction. When x is small, the result is large. 1 divided by 1/10th is 10. 1 divided by 100th is 100. 1 divided by 1,000,000th is 1,000,000. As x gets smaller, approaching zero, the result gets larger, approaching infinity. At exactly zero, the expression explodes. It doesn't equal any finite number. It equals, in some sense, infinity. But infinity isn't a number, so the expression is undefined. This matters enormously in physics because physical laws often involve division. Newton's law of gravity, for instance, describes the gravitational force between two objects. The force depends on the masses of the objects and the distance between them. Crucially, the force is inversely proportional to the square of the distance. Double the distance and the force drops to 1/4. Halve the distance and the force quadruples. But what happens as the distance approaches zero? What happens when two objects get infinitely close together? The force becomes infinite. The equation predicts an infinite gravitational attraction when two objects touch, when the distance between them vanishes. Obviously, this doesn't happen in reality. When you hold an apple, you're touching it. The distance between your hand and the apple is essentially zero, but the gravitational force isn't infinite. So what's going on? The answer is that Newton's law has limits. It's an approximation that works beautifully for objects at reasonable distances, but breaks down when objects get very close together. At very small distances, you can't treat objects as mathematical points. They have finite size. Atoms have extent. The distance between objects never actually reaches zero because the objects themselves take up space. The infinity in Newton's equation isn't a feature of reality. It's a signal that we've pushed the equation beyond its domain of validity. This pattern repeats throughout physics. Theories work within certain limits. Push them beyond those limits and infinities appear, warning signs that you've gone too far. The theory hasn't failed exactly. It's just telling you that it wasn't designed for this situation, that you need a different theory, a more complete description that handles the extreme case where the old theory breaks down. The most famous infinities in modern physics lurk inside black holes. Black holes are regions of space where gravity is so strong that nothing can escape, not even light. They form when massive stars collapse at the end of their lives, when the outward pressure from nuclear fusion can no longer balance the inward pull of gravity. The star implodes, crushing itself into an ever smaller volume, and if the star is massive enough, nothing can stop the collapse. The matter falls inward forever, or so our equations suggest. General relativity, Einstein's theory of gravity, describes black holes with remarkable precision. It predicts their properties, their behavior, their effects on surrounding space and time. But at the very center of a black hole, general relativity predicts something troubling: a singularity. All the matter that formed the black hole, all the mass and energy that fell into it, is compressed into a single point of zero volume and infinite density. Infinite density. Those words should set off alarm bells. Infinite density isn't a physical property. It's a mathematical abstraction, a sign that our equations have stopped making sense. What's really happening at the center of a black hole? We don't know. General relativity can't tell us, because general relativity breaks down there. The equations produce infinities, and infinities mean the theory has reached its limits. To understand what happens at a singularity, we need a theory that combines general relativity with quantum mechanics, a theory of quantum gravity. Such a theory would describe how gravity behaves at the smallest scales, where quantum effects become important. We have candidates for such a theory, string theory and loop quantum gravity being the most developed, but none of them are complete, and none have been experimentally tested. The singularity inside a black hole remains a mystery, hidden behind an event horizon that prevents any information from escaping. There's another singularity in physics, even more famous than black hole singularities: the Big Bang. Our best cosmological models tell us that the universe is expanding, that galaxies are moving apart, that space itself is stretching. Run this expansion backward in time, and you find that the universe was smaller in the past, denser, hotter. Keep running backward, and you reach a point, roughly 13.8 billion years ago, when the entire observable universe was compressed into a region of zero size and infinite density. Another singularity, another infinity, another breakdown of our equations. Was the Big Bang really a singularity? A moment of infinite density? Almost certainly not. Just as the singularity in Newton's gravity equation signals that we've pushed the theory too far, the Big Bang singularity signals that general relativity breaks down at the earliest moments of the universe. Before a certain point, called the Planck time, roughly 10 to the negative 43 seconds after the Big Bang, our current physics simply doesn't apply. We need quantum gravity to describe what happened. And without quantum gravity, we can't say whether the universe really had a beginning, whether time really started at the Big Bang, or whether something else, something our current theories can't describe, preceded the moment we call the origin of everything. Infinity appears in physics in more subtle ways too. Consider the electron, one of the fundamental particles of matter. An electron has electric charge, and that charge creates an electric field that extends outward in all directions. The field gets stronger as you approach the electron. Classical physics treats the electron as a point particle, a mathematical point with no spatial extent. But if the electron is truly a point, what is the electric field right at the electron's location? The field strength is inversely proportional to the square of the distance, just like gravity. At zero distance, the field should be infinite, and the energy stored in that field should also be infinite. This is called the self-energy problem, and it plagued physics for decades. How can an electron have infinite energy? Where would that energy come from? The answer from classical physics was unsatisfying. Just don't ask about distances smaller than some minimum. Treat the electron as if it had finite size, and ignore the infinities. But this felt like sweeping the problem under the rug rather than solving it. Quantum mechanics changed the picture, but didn't eliminate the infinities. In quantum field theory, the modern framework for describing particles and their interactions, electrons aren't really points. They're excitations in quantum fields, ripples in an underlying substrate that permeates all of space. But when physicists tried to calculate the properties of electrons using quantum field theory, infinities appeared again. Different infinities than the classical ones, but infinities nonetheless. The theory seemed to be giving nonsensical answers. The solution, developed in the 1940s and 50s by physicists including Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, is called renormalization. It's a mathematical procedure for handling the infinities that appear in quantum field theory. The basic idea is subtle, and to many physicists, philosophically troubling. You acknowledge that your theory produces infinities for certain quantities, but you notice that these infinities always appear in specific combinations. By carefully redefining certain quantities, absorbing the infinities into your definitions, you can extract finite, meaningful predictions. It works like this. The theory predicts an infinite value for, say, the electron's mass, but you can never measure the bare mass of an electron directly. You always measure the dressed mass, the mass that includes all the quantum corrections and interactions. The bare mass might be infinite, but the difference between the bare mass and the dressed mass is also infinite in just the right way that the physical, measurable mass comes out finite. You subtract infinity from infinity and get a finite answer. This sounds like cheating, like mathematical sleight of hand, and in some sense it is. Feynman himself, one of the architects of renormalization, called it a shell game. He said they had swept the difficulties under the rug and expressed hope that future theories would eliminate the infinities entirely. But here's the remarkable thing: renormalization works. It works incredibly well. The predictions of quantum electrodynamics, the quantum field theory of electrons and photons, agree with experiments to more than 10 decimal places. This is one of the most precise agreements between theory and experiment in all of science. Whatever philosophical misgivings we might have about subtracting infinities, the procedure gives answers that match reality with extraordinary accuracy. The infinities are there, lurking in the mathematics, but physicists have learned to work around them, extracting meaningful predictions despite the apparent nonsense. Not all infinities can be renormalized. However, some theories produce infinities that can't be absorbed or cancelled, that infect every prediction and render the theory useless. These theories are called non-renormalizable. General relativity, Einstein's theory of gravity, is non-renormalizable. When you try to apply quantum mechanics to gravity, infinities appear that can't be removed by any renormalization procedure. This is one of the reasons we don't have a complete theory of quantum gravity. The straightforward approach of combining general relativity and quantum mechanics produces a theory that makes no sense, a theory drowning in infinities that can't be tamed. There's another infinity in physics that might be the most severe of all: the cosmological constant problem. Empty space, according to quantum field theory, isn't really empty. It seethes with virtual particles, pairs of particles and antiparticles that pop into existence for the briefest instant before annihilating each other. This quantum vacuum has energy, called vacuum energy or zero-point energy. It's a consequence of the uncertainty principle, a fundamental feature of quantum mechanics. When physicists try to calculate how much vacuum energy empty space should have, they get an enormous number. Depending on how you do the calculation, it might be infinite, or it might be finite, but staggeringly large. The most conservative estimates give a value about 120 orders of magnitude larger than what we observe. That's a 1 followed by 120 zeros. This is often called the worst prediction in the history of physics. Our theories say the vacuum energy should be unimaginably huge. Observations say it's tiny. The mismatch is not a small discrepancy. It's a factor of 10 to the 120th power, a number so large that no analogy can capture it. We know the vacuum energy isn't actually that large, because if it were, the universe would behave very differently. Vacuum energy contributes to the cosmological constant, a term in Einstein's equations that affects the expansion of the universe. If the cosmological constant were as large as our calculations suggest, the universe would be expanding so rapidly that galaxies, stars, planets, atoms, everything would have been ripped apart long ago. The fact that we exist, that structures have formed, that the universe has evolved slowly enough for life to emerge, tells us the cosmological constant must be tiny. But our theories predict it should be enormous. Some unknown mechanism must be cancelling almost all of the vacuum energy, leaving only a tiny residue. But we have no idea what that mechanism is. It's one of the deepest unsolved problems in physics, a mystery that has resisted explanation for decades. The infinity of vacuum energy, or near infinity, or whatever it is, haunts our theories and mocks our attempts at understanding. Quantum mechanics introduces infinity in yet another way: the superposition principle. A quantum particle can exist in multiple states simultaneously. An electron can be in multiple places at once, or spinning in multiple directions at once, until a measurement forces it to choose. The wave function that describes a quantum particle extends across all of space, assigning a probability to each possible location. In principle, an electron could be anywhere in the universe. The wave function never quite reaches zero. No matter how far from the expected location you go, this is a kind of infinity. The infinity of possibility, of superposition, of quantum indeterminacy. Some interpretations of quantum mechanics take this infinity further. The many worlds interpretation, proposed by Hugh Everett in 1957, suggests that every quantum measurement splits the universe into multiple branches. When you measure an electron's position, you don't force it to choose one location, Instead, the universe splits into multiple versions, one for each possible outcome. In one branch, you observe the electron here. In another branch, you observe it there. All branches are equally real. If many worlds is correct, the number of universes is unimaginably vast. Every quantum event, every measurement, every interaction between particles spawns new branches. The multiverse grows exponentially, branch after branch after branch. By now, the number of branches is incomprehensibly large, and it grows larger every instant, perhaps infinitely large, if the process has been going on forever, if time extends infinitely into the past. Infinitely many versions of you, infinitely many versions of every event, every possibility realized somewhere in the endless tree of branching worlds. This is speculative, of course. Many worlds is one interpretation of quantum mechanics among several, and we have no way to test which interpretation is correct. The branches, if they exist, are forever isolated from each other. You can never observe the other versions of yourself, never confirm that the multiverse is real, but the possibility is there, suggested by our best theory of the microscopic world, another way that infinity might be woven into the fabric of reality. What should we make of all these infinities in physics? Some physicists see them as evidence that our theories are incomplete, that we're missing something fundamental about how the universe works. The infinities are clues, signposts pointing toward deeper truths we haven't yet discovered. Perhaps a future theory, a theory of quantum gravity, a theory of everything, will explain away the infinities, showing them to be artifacts of our incomplete understanding rather than features of reality. Other physicists are more accepting. They see the infinities as a natural consequence of applying mathematical idealizations to a physical world that never quite matches those idealizations. Point particles are mathematical conveniences, not literal descriptions of reality. The infinities that arise from point particles are prices we pay for the convenience, not signs of deep problems. As long as we can renormalize, as long as we can extract finite predictions that match experiments, the infinities are manageable. They're not failures, but features, aspects of how our mathematical tools interact with physical reality. And some physicists wonder if infinity might actually be out there. If the universe itself might be genuinely infinite in some way. Perhaps space really does extend forever. Perhaps there really are infinitely many branches of the quantum multiverse. Perhaps infinity isn't just a mathematical abstraction, but a physical reality, a feature of the cosmos we inhabit. The infinities in our equations might not be breakdowns at all. They might be glimpses of something true, hints that the universe is larger and stranger than our finite minds can fully grasp. Physics hasn't tamed infinity. It has learned to live with it, to work around it, to extract useful predictions despite the infinities that lurk in the equations. But the infinities remain, unsolved puzzles at the heart of our deepest theories. Every time a physicist encounters an infinity, they're reminded that our understanding is incomplete, that there's more to discover, that the universe still holds secrets we haven't penetrated. Infinity in physics isn't a destination, it's a frontier, a boundary marking the edge of what we know and the beginning of what we don't. We've traveled far on this journey through infinity. We began with the simple act of counting, the childhood discovery that numbers never end. We explored ancient paradoxes that tortured philosophers for millennia. We met Cantor, the man who dared to count infinity, who proved that some infinities are larger than others, and who paid for his audacity with his sanity. We visited Hilbert's Infinite Hotel, where the impossible becomes routine and arithmetic breaks down. We contemplated infinite space, infinite time, infinities in physics that mark the boundaries of our knowledge. But we haven't yet asked the most personal question of all. What does infinity mean for us? What does it tell us about who we are, about the nature of consciousness, about the possibility of God, about the meaning of existence itself? Infinity isn't just a mathematical concept or a physical speculation. It's an idea that touches the deepest questions humans have ever asked. And it's time to face those questions directly. For most of human history, infinity was not a mathematical concept. It was a theological one. Infinity belonged to God. Only God was truly infinite. Infinite in power, infinite in knowledge, infinite in goodness, infinite in duration. Creation was finite, limited, bounded. Only the Creator was without limits. This association between infinity and divinity runs through almost every religious tradition. The Judeo-Christian God is described as eternal, existing outside of time, with no beginning and no end. The Hindu concept of Brahman, the ultimate reality underlying all existence, is described as infinite, all-pervading, beyond all limitation. Islamic theology emphasizes Allah's infinite attributes, qualities that have no bound or measure. Even in traditions that don't focus on a personal God, infinity appears as a marker of the ultimate, the transcendent, the sacred. This religious understanding of infinity shaped how people thought about it for millennia. Infinity was not something humans could fully comprehend, because it belonged to a realm beyond human understanding. It was not something humans could possess or control, because it was the exclusive property of the divine. To claim human access to infinity, to study it as mathematicians now do, would have seemed presumptuous, perhaps even blasphemous. How could finite creatures grasp the infinite? How could limited minds comprehend the unlimited? The attempt seemed doomed to failure, or worse, to the kind of hubris that myths warned against. Cantor saw his work differently. He was deeply religious, and he believed his mathematical discoveries were revelations from God. The transfinite numbers, the hierarchy of infinities, the strange and beautiful structures he uncovered, these were not human inventions, they were divine truths, aspects of God's infinite nature that God had chosen to reveal through mathematics. Cantor corresponded with theologians, seeking their approval, wanting them to recognize that his work supported rather than undermined faith. He saw himself as a humble instrument, a vessel through which divine truth entered the human world. Not everyone agreed. Some theologians worried that Cantor's infinities competed with God's infinity. If there were many infinities arranged in a hierarchy, each larger than the last, what did that mean for divine infinity? Was God's infinity just another level in Cantor's tower, or was it something different, something beyond all mathematical infinities? These questions have no easy answers. Some religious thinkers embraced Cantor's work, seeing it as a deepening of our understanding of infinity. Others remained suspicious, sensing that mathematical infinity might be a different kind of thing than theological infinity. Related perhaps, but not identical. The relationship between mathematical and theological infinity remains unresolved. Mathematicians study infinite sets, infinite numbers, infinite structures. These are precise, well-defined objects, subject to rigorous proof. Theologians speak of divine infinity, an infinity that is not just large, but qualitatively different from anything finite, an infinity that encompasses all perfections, all possibilities, all being. Whether these two concepts of infinity are the same, or related, or entirely different, is a question that neither mathematics nor theology can definitively answer. It depends on what you believe about the nature of God, the nature of mathematics, and the relationship between abstract structures and ultimate reality. But even setting aside theology, infinity raises profound questions about the human mind. Can we really understand infinity? Can finite creatures like us truly grasp the infinite? Our brains are physical objects, made of neurons and synapses, electrochemical signals propagating through biological tissue. The human brain contains roughly 86 billion neurons, a large number, but definitely finite. The number of possible brain states is enormous, perhaps larger than the number of atoms in the observable universe, but still finite. How can a finite system comprehend infinity? One answer is that we don't really understand infinity. We manipulate symbols, follow rules, prove theorems. We can write down the symbol for infinity. We can state definitions and verify proofs, but genuine understanding, the kind of intuitive grasp we have of small numbers and everyday objects, might be forever out of reach. When you see 3 apples, you understand threeness directly, immediately, without calculation. But when you contemplate Aleph Null or the continuum, there's no direct intuition. There's only the formal apparatus, the definitions and theorems. the symbolic manipulation that serves as a substitute for genuine understanding. Some philosophers argue that this is enough. Understanding is not the same as visualization or intuition. We understand many things we cannot visualize: higher dimensional spaces, quantum superposition, curved space-time. We understand them through mathematics, through formal descriptions that capture their properties, even if we can't picture them in our minds. Infinity might be the same. We understand it formally, mathematically, even if we lack intuitive access to it. The formal understanding is genuine understanding, not a second-rate substitute. Others are less sure. They suspect that our formal manipulations of infinity are like the manipulations of a calculating machine, following rules without genuine comprehension. We can prove that some infinities are larger than others, but do we really understand what that means? Or are we just shuffling symbols according to syntactic rules, getting correct answers without any deeper insight? The question is related to broader debates in philosophy of mind about the nature of understanding and whether it can be reduced to computation. These debates have no resolution, and the nature of our understanding of infinity remains genuinely puzzling. There's a deeper question still. Does infinity tell us something about the limits of human knowledge itself? In the early 20th century, mathematicians hoped to establish mathematics on an absolutely secure foundation. They wanted to prove that mathematics was consistent, that it contained no contradictions, and complete, that every true statement could be proved. This program, associated with David Hilbert, seemed achievable. Mathematics was the most rigorous of disciplines. Surely it could be shown to be solid all the way down. In 1931, Kurt Gödel shattered this dream. He proved two theorems that changed mathematics forever. The first incompleteness theorem showed that any consistent mathematical system capable of expressing basic arithmetic contains true statements that cannot be proved within the system. Mathematics is necessarily incomplete. There will always be truths beyond the reach of proof. The second incompleteness theorem showed that no such system can prove its own consistency. If mathematics is consistent, we can never prove it using mathematical methods alone. We have to take consistency on faith, or establish it by methods outside the system. Gödel's theorems don't mention infinity directly, but they're deeply connected to it. The true but unprovable statements Gödel constructed are related to self-reference and the infinite regress of meta-languages, talking about languages. The continuum hypothesis, which we discussed earlier, is an example of a statement independent of standard mathematics. We can't prove it or disprove it from the usual axioms. It's not just that we haven't found a proof. There is no proof to find within the system. Mathematics contains fundamental gaps, questions it cannot answer, limits it cannot transcend. This might be seen as a defeat, a limitation on human reason. We hoped mathematics could be complete and perfect. It can't. There are truths beyond our reach, questions we can formulate but never answer. Infinity, which generated many of these unanswerable questions, has revealed the boundaries of mathematical knowledge itself. But there's another way to see it. The incompleteness results don't show that mathematics is weak. They show that mathematics is inexhaustible. There will always be more to discover, more truths to uncover, more territory to explore. Mathematics isn't a finite building that could someday be completed. It's an infinite landscape that we'll never finish mapping. This is exhilarating, not depressing. It means mathematics will never be done. There will always be work for mathematicians, always mysteries to solve, always wonders to find. Infinity guarantees that the journey continues forever. What about meaning? In an infinite universe, does anything matter? This is perhaps the most personal question of all, and it's one that infinity seems to threaten. If space is infinite, containing infinitely many galaxies, stars, planets, perhaps infinitely many civilizations, what makes us special? We're one planet among infinitely many, one species among perhaps infinitely many intelligent species, one moment in infinite time. Our concerns, our achievements, our entire existence vanish into the infinite like a drop in an ocean without shores. The philosopher Blaise Pascal felt this vertigo intensely. In his Pensées, written in the 17th century, he described the terror of infinite spaces. the silence of the infinite universe that filled him with dread. He saw humanity suspended between two infinities, the infinitely large and the infinitely small, unable to comprehend either, lost in a cosmos that dwarfed all human meaning. For Pascal, the only escape from this existential terror was religious faith, a leap beyond reason into the arms of a God who conferred meaning on the meaningless. But not everyone shares Pascal's terror. Some find infinity liberating rather than threatening. Yes, we're small. Yes, our existence is brief. Yes, the universe is vast beyond comprehension. But so what? Meaning doesn't require cosmic significance. The love you feel for your family is meaningful. Whether or not the universe is infinite, the beauty of a sunset is real, whether or not there are infinitely many sunsets on infinitely many worlds. The satisfaction of understanding, of creating, of connecting with others, these things have value in themselves, independent of scale. In fact, infinity might enhance meaning rather than diminish it. In a finite universe, everything would be countable, measurable, exhaustible. Eventually, everything would be done. Every experience would be had. Every possibility would be realized. And then what? A kind of cosmic completion, perhaps. But also a cosmic closure. Nothing new under the sun. Nothing more to discover. Nothing left to become. But in an infinite universe, there's always more. Always another galaxy to explore. Another question to ask. Another mystery to solve. Infinite possibility. Infinite potential. The journey never ends, because there's always more road ahead. The writer Jorge Luis Borges explored this idea in many of his stories. In The Library of Babel, he imagined a library containing every possible book, every possible arrangement of letters, infinitely many volumes. At first this seems wonderful, all knowledge contained in one place. But Borges shows the horror of it. In an infinite library of random books, finding anything meaningful is nearly impossible. Most books are gibberish. Even the books that contain truth are buried among infinitely many books that contain falsehood. Meaning is diluted to nothing in the ocean of infinity. But Borges also saw the other side. In some of his stories, infinity is not a threat, but a promise. The garden of forking paths, where every possibility is realized. The Aleph, a point in space that contains all other points, all of infinity, compressed into a single location. These images suggest that infinity might be encountered, engaged, even loved, rather than merely feared. Infinity is not just the enemy of meaning. It might also be its secret source, the inexhaustible well from which meaning endlessly springs. Let's return, finally, to where we began, counting. 1, 2, 3, 4, 5. The simplest mathematical act, the first abstraction every child learns. When you count, you participate in something infinite. The numbers go on forever. There's no end to them. Every number has a successor. The chain extends beyond any horizon you can imagine. This infinity isn't threatening, it's familiar. You've lived with it since childhood. You take it for granted, and yet it contains, in embryonic form, all the infinities we've explored. The hierarchy of cardinalities, the paradoxes of Zeno and Galileo and Cantor, the unanswerable questions and undecidable propositions, the possible infinity of space and time, the infinities that haunt physics, the infinite that religious traditions identify with the divine. All of it begins with counting. All of it flows from the simple observation that numbers don't stop. You are a finite creature. You will live for a finite time, experience finite events, think finite thoughts. Your brain has finite capacity. Your life has finite duration. You will never count to infinity. You will never traverse infinite space or infinite time. In every concrete, practical sense, you are limited, bounded, small. But you can think about infinity. You can understand, at least formally, what infinite means. You can follow Cantor's proofs and grasp that some infinities are larger than others. You can appreciate the strangeness of Hilbert's Hotel and the paradoxes of Zeno. You can contemplate infinite space and infinite time, the infinite past and the infinite future, the infinite hierarchy of mathematical structures rising forever beyond your comprehension. You can hold infinity in your mind, not all of it, not most of it, but a glimpse, a shadow, a reflection. This is remarkable. This is, in its way, miraculous. A finite being, contemplating the infinite. A brief spark of consciousness, comprehending eternity. A creature of limits, reaching toward the unlimited. We are bridges between the finite and the infinite, not fully belonging to either realm, but participating in both. Maybe that's what infinity ultimately teaches us. Not our smallness, though we are small. Not our ignorance, though there is much we don't know, but our strange position in the cosmos. Finite beings with infinite reach, limited creatures with unlimited curiosity, mortal minds that can think eternal thoughts. We are the universe's way of contemplating itself, and in contemplating infinity, we touch something that transcends our limitations. When you look up at the night sky, you see finite points of light, each one a distant sun, but you know that the sky might extend forever, that the stars might continue without end, that infinity might be out there, waiting, stretching beyond every horizon. And you know that you can think about it, reason about it, wonder about it. The infinity doesn't diminish you. Your comprehension doesn't exhaust it. You and infinity coexist, the finite and the infinite intertwined in the act of contemplation. Infinity breaks our brains. Yes, it defies our intuitions, shatters our expectations, reveals the limits of our understanding. But it also elevates us. It shows us that there's more than we can ever know, more than we can ever experience, more than we can ever be. And somehow, despite our smallness, we can reach toward it. We can ask questions about it. We can prove theorems and contemplate mysteries and wonder at the vastness of it all. That reaching, that wondering, that endless question, what comes next, what lies beyond, how much more is there? That is the human encounter with infinity. It doesn't end, it can't end, because infinity, by its very nature, goes on forever, and as long as there are minds to contemplate it, the journey continues. Thank you for taking this journey with me. We've traveled from counting to canter, from Zeno to black holes, from Hilbert's Hotel to the meaning of existence. We've seen infinity in numbers and space and time, in physics and philosophy and theology. We've confronted paradoxes that have no easy solutions and questions that have no final answers. But the journey isn't over. It can't be over. Because infinity has no end. There's always more to explore, more to understand, more to wonder at. The next question is always waiting. The next mystery is always beckoning. The next infinity is always just beyond the horizon. May you never think about counting the same way again. May you never look at the night sky without wondering if it goes on forever. May you carry with you a sense of the infinite, not as a threat to meaning, but as its inexhaustible source. You are finite, you are brief, you are small, but you can think about infinity. And in that thinking, you participate in something larger than yourself, something that will never end, something that stretches beyond every boundary and transcends every limit. That's what infinity gives us. Not answers, but questions. Not completion, but continuation. Not an end to wonder, but wonder without end. Good night, and may you never stop counting.